És hogy kell a... És mivel? Lelépett. Szuper. Köszi. Tessék? Nem, szerintem nyugodtan várd meg a 6-9-et. Most ez a 2 percet nem tudom. Utána mi van? Utána ki van? És utána? Aha. És mikor van a Ágoston? Ugye nem adott be? Ágoston nem ad elő. Ja, értem. Oké.
Okay, welcome everyone for the second day of the GPU days of 2022. Let's begin our first section, and the first lecturer is Zoltán Zimvarás from Wigner Research Center for Physics, and he will talk about photonic quantum simulator software, a framework for optical quantum computer programming and simulation. Thank you.
Thanks a lot, Balázs, for the kind introduction. And indeed, in this morning session, this will be devoted to quantum computing and HPC. And actually, with Gergely, together with Gergely, we have been striving through that in the GPU days, there should be blocks about the intersection between high performance computing and quantum computing for some years now. And we also have some, by the way, some joint research grants on this. And in that context, I would like to give a presentation about a project which is actually 1.5 years old, and it's just finished, at least like with the first version, namely our Picasso software, and there will be some consecutive talks after mine talk, and also in other later sessions, which will deal with the specifics of this. So this software framework is called Picasso. It's an abbreviation for Photonic Quantum Simulator Software. And as the title suggests, it's a framework for optical quantum computer programming and simulation. And what is like optical quantum computing? I mean, quantum computing has been now in the focus of attention of various researchers and companies. Here I mean IBM, Google, Alibaba, PsiQuantum, and so on, Microsoft, and also famous research institutes. And often what the public is exposed to is the qubit-based and gauge-based quantum computation, where you have two, so each constituent, let's say a superconducting qubit, has two well-separated states, a two-level system, and you can have any superposition of that. And then if you take many qubits, then you have you will get this big quantum mechanical state space, which is the superposition of like multi-qubit states. On the other hand, there are also very promising directions of photonic quantum computation or research. And this is like Q mode based, and our simulator is Q mode based. Here, what you have is that actually you should imagine it in this way, that you have an integrated chip where there are photonic states in the input. There is like quantum light sources. I will talk about what are the typical sources. And then there are like gates, like when two of those quantum light states meet, let's say two photons, there are like interferometric gates, and you can have also measurements and nonlinearities induced by measurements, and then single photon detectors. and actually some of the hardware developers are working with this with great success. In particular, one is Xanadu, and then other one is PsiQuantum, and well, Candela is doing the quantum light sources. So this is a very promising direction. And actually, people have heard about the famous IBM quantum supremacy experiment, but there has been quantum supremacy experiments performed also with photonic quantum computers. In particular, there were two experiments made by the Hi-Fi group in China, the same group that was performing this also famous quantum satellite experiments when they had quantum communication between Vienna and China, and space-based quantum communication. And also there was a very nice experiments done maybe 2 weeks ago by Xanadu, which also showed supremacy using this Q-mode-based quantum computation. And of course, when the hardware vendors are developing these quantum computers, and there are also clouds coming up, there are different type of quantum simulators and quantum programming languages popping up. There is a huge competition there. For example, if you think about the qubit-based models, there is the famous Qiskit programming framework by IBM. Also, Google has its own, the Cirque. Then there is a different one, the Q-Sharp by Microsoft. And there is a huge competition there. On the other hand, for the Q-mode-based quantum computing, there are actually not so many programming languages available. Basically, maybe one or two. One is Xanadu's Strawberry Fields, and another one where you can use, but it's more like the physicist-based language, like mostly for not exactly for quantum computation in this context, it's Qtip. So our idea was that actually there is a market gap here, and we should try to build it. And it was very easy to convince people to build it, because there were many. I mean, it was obvious when we showed this market gap for that people joined, and also organizations joined. So this was then done as a part of the Quantum Information National Laboratory of Hungary, in particular Wigner Research Center for Physics was involved, and Eötvös University. And actually, we also got support from Ericsson, and also we had some international collaboration, namely from the Academy of Sciences of Poland, Michał Ośmaniak and Tomek Tybocki. And so here are the main contributors, Wigner, Ötvös University, Ericsson. And, here you can see the different type of, let's say, components of this package. So first of all, like we have Picasso, which is a high-level Python programming interface for coding Q-mode systems. Then we have for this UI system, there is a very nice graphical user interface, and it's online access. By the way, you can see this Picasso.com works, and you can go there. And also we have a Picasso boost, which is nicely connected to the Python programming interface, which is actually a high-performance C++ computing engine. And we have also we have produced papers which go beyond state-of-the-art result, like it produces going beyond state-of-the-art results with this Picasso boost. And actually, we also have a new module which is yet unpublished, which is the Picasso data flow engine. So here we have a FPGA-based data flow engine support for quantum computation simulation, and we will have our own talk about that. And this was done actually in collaboration with the Maxeler Technologies, which is a startup actually working on data flow engines and FPGAs. And actually, it was recently bought by Grok, which is like a startup that, or a spin-off from Google. It was started by the people who were developing the TPUs, the tensor processing units, at there, and now also they acquired Maxeler. I mean, here is I don't want to talk too much about this. It's a schematic picture about how we should imagine it. That there is a high-level Python API, and then it's then you see these connections to C+ libraries and so on. And just I flashed this out. Here you can see in the Picasso.com, you will see this type of very nice user interface where you can have a drag and drop simulator. There are different type of photonic gates that you can put in, and then the results can be visualized very nice. Let's say the probabilities of the different outcomes on detectors, say. And you can also see a code snippet, a Python code, how you can code. And actually, well, yes, I mean, as I told you, you can code Picasso in Python, but of course, this UI produces an automatic Python code in that language. Okay, and we don't only want to use this framework for quantum simulation and quantum programming with some classical hardware that provides a simulator, but also connected to real quantum hardware, quantum computers. I mean, one obvious possibility is that the Ötvös University acquired an 8x8 photonic quantum interferometer, and that would be an obvious possibility to integrate our code with that. But we also hope that maybe the company that has produced these quicks will take our software, and we can also integrate it with bigger quantum computers. So one thing, so our code and our programming framework is very well suited for simulating universal quantum computation. Zoltán Kolarowski, who is next after me, will talk about what type of tricks we did to beat our competitors in speed. But I want to focus on a particular set of problems, like not the universal quantum computation, but the problem of boson sampling. So this is boson sampling goes with these recent near-term algorithms that are like sampling algorithms that can show quantum supremacy even in near-term quantum computers. I mean, the Google experiment was such a sampling experiment, not boson sampling, but random circuit sampling. And as I told you, there are these hi-fi experiments and Xanadu experiments showing quantum supremacy. And that was done with boson sampling. Actually, there are various versions of boson sampling. The usual one is that you put in one photon state as the source into each of the modes. Then they go through a scattering process with this interferometer, and then you measure photon numbers. And in that case, you have to calculate the probabilities, like the output probabilities will actually be they will be proportional to the permanent of a matrix, which is somehow built out of this unitary matrix. Also, it depends what you measured here. So you build a matrix and take the permanent of that. And like the permanent, if you look at the permanent of a matrix, it looks like the definition looks like the determinant. Actually, like a -1 factor is missing, -1 to the power of the sign of the permutation, and that's missing from that. But it's much harder to calculate the permanent than the determinant. Like the permanent for an n by n matrix, it takes 2 to the time to calculate that. It goes as 2 to the n. Right. And if on the other hand, your detectors don't have a particle resolution, they just click if there is a 1 photon state, a 2 photon state, or 3 photon state, and don't click if it's a 0 photon state, then you have to calculate something called the Torontonian, which is a sum of exponentially many, like 1/√² of determinants. And finally, if you plug in not 1 photon states, but sort of coherent states, but you still measure particle number here at the end, then you have to calculate something which is like the Hafnian of the matrix, which is like has a relation to the permanent in the same relation as the so-called Pfaffian to the determinant, actually. And all these are known to be like hard functions. So each of them have exponential complexity. And but many of them, or actually all of them, have very nice relations to other mathematical problems, perfect matchings in graphs, and so on. And because of this, you can also build useful algorithms for this. And one is this like graph isomorphism using boson sampling. There was this idea. Another idea is the molecular docking using Gaussian boson sampling. And also you can calculate with boson sampling that produces a molecular vibronic spectra. Of course, I have to stress here that there is no proof that actually you get speed up using boson sampling, because there are also quite efficient other classical algorithms that calculates these. So this is an open question whether you can really have a useful quantum advantage. You can have a quantum advantage in boson sampling, but the useful one that's a question still. And right, and here you can see like that what the computational complexity of this of like calculating permanence, and also of doing boson sampling is. Like it goes 2 to the n asymptotically and also a squared factor. And as I told you, we have many ways of attacking it. There will be a talk about this data flow engine, FPGA-based data flow engines that will calculate very fast the boson sampling. Gregory will talk about it, but I just show here that we have this FPGA here. It's from Utrecht University, but we also have it at Wigner, such an engine, and you can see like that how it goes for 20 photons, 30 photons, and 36 photons. You have like 0.01. It takes 0.01 seconds to get one sample. Even for 36 photons, it takes 40 seconds. And another thing that I want to just highlight is that we can also use the C++ engine to obtain some speed up over state-of-the-art quantum simulators, namely the strawberry fields, and within the strawberry fields, the walrus. And for example, calculating the Gaussian boson sampling, you will get a 6-8 times speed up. Yes, so, and actually this is what I would like to conclude with this slide. And if somebody is interested in joining our work, you are very welcome. And if somebody is interested in the code package and playing with it, then go to the Picasso.org homepage. Which was, where was this? Picasso.com. Yeah, I think it should also work. Okay, thank you very much.
Thank you very much for the interesting lecture. And there is are there any questions?
A funny question: bosonic or fermionic? Which is
actually, so the thing is that that's a funny question. So let me tell you why it's a funny question. So basically, people were thinking of doing, why don't people do this with fermions, doing fermion sampling? And there is a very easy answer to that, namely that because there the output probabilities would be proportional to a submatrix of this unitary matrix and the determinant of that submatrix. And the determinants are fast to calculate, and that's why Scott Arens and other people said that fermion sampling is not a good scheme for quantum supremacy. But I have a paper on that because we actually tweaked the scheme only a little bit. What we did was that we added here added one fermion states, a couple of one fermion states, and a couple of zeros, like as many zeros and ones, and then we took like one layer of gates here, like two fermion gates, and it turned out that in that case you can actually get probabilities that are proportional to something called the mixed discriminant, and actually some versions of the mixed discriminants give you back the permanent, and that's also hard. So also fermion sampling could work, but that you should simulate with qubit-based quantum computers. Like directly simulating it with fermions is also very interesting, but it's harder to handle fermions in a quantum manner, like in experiments.
What is the main focus of your research now? I mean, which problem do you want to solve with this?
So, I mean, this is what we did here was mostly it was a tool for us. We built a tool for us and also for other people that can use like you can have a photonic quantum computer simulator. And as I told, this is, I would say, it's faster and also more flexible than the current one. As I mentioned in the talk, there are lots of very flexible and good quantum computer simulation for qubit-based quantum computers, but not for photonic ones. We are also working on doing some theoretical work on how to speed up, in principle, calculating Torontonian permanence, looking where is the, let's say, where is the boundary between quantum supremacy and something that you can simulate classically. For instance, with Agoston and Zoli, who are here, we are hoping to prove that Gaussian boson sampling, so the Hafnian one, it doesn't give advantage if you have a logarithmic depth only, like you have n q modes and log n depth and such things like that. But we also, maybe I didn't stress enough, but we are also having some works on applying this boson sampling to problems. Let's say Peter Rakita has a project that wants to solve QUBO problems with it, for example, and so on. These are our focuses with this, but we also do, like in the group, we do also regular quantum computing and quantum algorithm research, also not necessarily based on quantum photonic quantum computers. One thing which is really missing here, yeah, I forgot this, great that you asked me, that we are working on quantum machine learning, and we want to adapt our package, the Picasso package, also that maybe TensorFlow could run on it, or it will be compatible on with TensorFlow, and we could do variational quantum circuits, quantum machine learning.
So I just wanted to ask about if there's any equivalence that's been shown between the qubit, an algorithm that's done with qubits versus Q mode. You know, similar to, you know, NP complexity problems can be polynomial transformed. Is there any way that, you know, any qubit algorithm could be transformed into a Q mode like problem?
That, yes.
Or reverse?
Mm-hmm. Yes, so the reverse is a little bit more complicated, but that's a very good question. Thanks a lot. And yes, there is. This is called like the most famous one of them is called the KLM scheme, Neil, Laflamme, Milburn. There are 3 persons, and where you use a dual rail encoding. So you really mimic qubits, like you have for each qubit, you have 2 Q modes. It's a waste of resources, but I mean, it still works. Like a 1 photon in the first qubit and 0 in the other would mean like the 0 state, and 0 in the first and 1 in the second would be in the 1 state, and then you can actually couple them and completely simulate. The other way around is much more complicated, and it's maybe not. You have to formulate it very well, because look, in photonic, in what you are used to usually in qubit-based quantum computation, that you can reach basically any state, or you can start from any state, or locally any state. But here, even locally for 1 photon, you cannot plug in the state like a 100 photon state or a 1000 photon state. You cannot produce it experimentally. So what you have to work with are experimental limitations, like 1 photon states, coherent states, some things like that. And you can do an equivalence if you do some cutoff in the, let's say, energy, or make a cutoff in the particle number. Then you can make an equivalence between those computations. But usually what they do is that they have this embedding of qubit-based quantum computation into optical quantum computation, and this is the Neil, Laflamme, Milburn scheme. By the way, we have also a student who works on the generalization of that.
Thank you for the questions, and thank you, Timbi, for
Thank you very much.
Nice lecture. Our next lecturer is Zoltán Kolárovszky.
Do you hear me? I think
Yes.
you do. Okay. Hi, everyone. I'm Zoltán Klarowski. I am a PhD student at Eötvös Loránd University, and I also work at Wigner part-time. And today I will talk about improving efficiency of a non-Gaussian photonic circuit. It's actually a cute computational trick that we have discovered, and it came very naturally, and it turned out to be really efficient compared to the existing solutions that we have. The outline of this talk, I will talk about how to model optical circuits, some bit of mathematics about it, and then I will talk about the naive tensorial computation, which has been done previously. And we have this proposed computation where we did this trick, and then we will at the end compare the two computations. Okay, so let's start modeling an optical circuit. Here you can see on the diagram. Do I have this? Maybe this works. This doesn't work. How does this work? I will need that. Oh, so but there's no pointer. Okay. Anyway, so here you can see on the diagram that the photonic circuit consists of an initial state, and then you apply some gate state. You evolve the system to get the final state. You will have you can have more complicated stuff like measurements, but we won't deal with that. So we didn't really use this trick at that. So you can model single particles on a QMO, an orthonormal basis vectors, or a set of orthonormal basis vectors, and this is the E0 goes to ED minus 1. So for example, you can see that the E2 corresponds to a single particle on the second mode. To build multi-particle Fock basis states, you can symmetrically tensor multiply these. So you use the symmetric tensor product. I don't really want to introduce the symmetric tensor product. We don't really need that. But the interesting thing is that the number of exponents, so to say, the tensor product exponents will be become the state actually. So we will use this notation where you can see in the example that the exponents are 1, 3, and 0, and this will become 1, 3, 0. This is just a notation actually. And the another concept which we will need is the number of particles. In the case of Fock basis states, we just sum the integers in this, or equivalently sum the exponents in the basis vectors. And this is the number of particles. And you can see that if we fix the number of particles to n, and we have d modes actually, then the number of Fock basis states we will have is just a combinatorial expression. And you can expect that if you have a large number of modes and you have many particles, then this will grow exponentially. Okay, the next thing is that we can create quantum states using combinations of these Fock basis states. The only catch is that the square of the coefficients need to sum up to 1. They have a probability interpretation. And the generic pure state can be written as seen in the equation 5, where each Cn is a complex number actually. And we actually need to store, if we want to simulate it, we need to store these Cn's in the computer. But as you can see, apparently there are infinitely many of them. The next thing which we need to consider is the quantum gates. So quantum gates are essentially maps between Fock basis states. Like for example, here the beam splitter acts on the 1, 0 state as cos theta of 1, 0 and sin theta of 0, 1. That is very easy. And you can generally write a quantum gate by their coefficients actually. So during computation, you will need to store the coefficients, and you will have some rules regarding how to evolve the state with this gate by their coefficients. Okay, but as I have mentioned, there are infinitely many of these coefficients. And Tsimby also said that we need to introduce a cutoff of some sort. And the naive cutoff, which people initially did, is that we can cut off the maximum number of particles mode by mode. I call this the mode by mode cutoff. With this consideration, you can see that in the equation 8, that the CN coefficients, the number of them is finite because the sum is a finite. It's a finite sum. With this prescription, we will have c to the power of d many coefficients. And as an example, you can see that the Fogg basis states 2, 3, 4 can be simulated for the cutoff equal to 5, while 5, 6, 7 couldn't, because 7 is larger than 5. Okay, that was very simple. One drawback of this tensorial computation is that c to the power of d could be huge, actually. So let us consider a case where we do a computation with 7 modes and 5 as a cutoff. It's very conservative, so to say. So it's not a large system. But if we want to store a quantum gate, so a large quantum gate of size 7, then we would need to have 90.9 gigabytes of memory to do that. So yeah, there must be an economical way to do this, a more economical way. And that is what we will consider now. But first, let's talk about active and passive gates, because this discussion will lead us to the newly devised computation. The beam splitter gate, as you have seen before, there's a computation. It conserves the particle number. So it maps 1, 0 state into 1, 0 or a 0, 1 state. It does nothing to the total number of particles. However, there are actually quantum gates which do not preserve the number of particles. For example, the displacement gate. This is actually also called the coherent state. Gates which conserve the number of particles are called passive gates. Gates which do not conserve it, create or annihilate particles, they are called active gates. We can do a matrix representation of the computation. So we can map the 1, 0 state into a vector of 1, 0, for example, and similarly for the 0, 1. And if we do that, then we need to represent, for example, this passive beam splitter gate as a matrix. We can do that, and we can compute with that. But the catch is that for multi-particle states, so if we have multiple particles, then we obviously will have larger matrices, because if you consider that you can have multiple particles, there are much more Fogg basis states, actually. And actually, it can be seen that this is a combinatorial expression. It's actually a combination with replacements, if you consider it. That many basis vectors we will have. And the quantum gates can be calculated by equation 14. And these are actually huge matrices, but still much smaller than the c to the power of d matrices or tensors. And if we want to compute with this passive gate, then we need to produce all of the matrices which act on all of the particle number subspaces, actually. So, for example, you can see that the G1 is for the one particle scenario. G to the 1 on the symmetric tensor power of 2 acts on 2 particles, and so on. So you can infinitely continue this matrix. This is a block matrix, or yeah. But you can see here that you have infinitely many of these blocks. So naturally, what we did is that we cut this off. So we imposed a system-wide cutoff for the total particle number. So we put the C in the direct sum instead of the other sum with the states before in the tensorial computation. So we cut along the line, as you can see. This is actually for C equal to 3, I think. And you can see that the dimension of this matrix is, again, this combinatorial expression, but is much smaller. And we will see this. So they consider the same scenario which we did with the cutoff equal to 5 and the number of modes equal to 7. And if you consider this, the memory usage of this quantum gate is 1.66 megabytes, which is, okay, it's not small because it's a matrix, but it is negligible in comparison with the 90.9 gigabytes, which we obtained previously by the tensorial computation. But there's a catch here, that it is a worse approximation, because we cut off more Fock basis states than we did before. For example, if you have C equal to 5, then the 3, 4, 3, and 2 Fock basis state is contained. It's very symbolical what I have written here, but it is contained within the mode by mode cutoff. We simulate this because each of the numbers are less than 5. But in the system-wide cutoff, we don't consider it. So it is much smaller. But there's an argument for the system-wide cutoff that, for example, for active gates, the high contributions from higher particle numbers are usually small. So you can see that this display state, this coherent state, which you can see on equation 16, has this equation, and you can compute the particle number detection probabilities easily, and you will have this equation for the probability distribution. I think that is a Poisson distribution, which quickly decreases to 0. Similar argument can be done for many other systems, but I should emphasize that not all systems. So you can consider a case where it is not so good because you want to simulate like 4, 4, 4, 4, 4 Fock basis states. Then it's not really good, the system-wide cutoff. But usually people don't do that. And the second argument for system-wide cutoff is that if you have initial states as Fock basis states and you have passive gates, then the number of particles are obviously conserved, and we will get the same results for every computation if we choose the cutoff wisely. And we will have precise results this way. And we have seen already that the memory usage is significantly reduced, and we can show the same for the computation time. Here I have written a simple circuit where we have used 1, 0, 1, 0, and so on states, and the number of particles is V/2, and the ceiling there. And I have used 2 columns of Kerr gates. It's not that it's a meaningful computation. It's not, but for benchmarking it is fine actually. And we have shown that the computation times of Picasso is much smaller than the strawberry field computations, which uses the tensorial computation scheme. Here I should note that I couldn't do many simulations with the strawberry fields one because, as you have seen before, at the mode number of 7, I would have needed 90.9 gigabytes of memory, but my computer only has like 32. So yeah, I had to cut off that because it didn't run. But Picasso runs. Picasso doesn't use that much memory, apparently. 6. That many I have in my computer. It's rapidly increasing because it's c to the power of d, and c for 6 is like 3, I think, or 4. Yeah, it is much smaller, so it scales exponentially, very fastly. This tensorial computation, the Picasso is much lower, so we could go on further with that. We hit the exponential wall much later. We hit the exponential wall, so it's still exponential. It's not that great, but it's better. And that is it. Thank you for your attention.
Thank you for this nice lecture. Are there any questions?
Thank you for your presentation, Zoltan. I have a general question for you. How far do you think we are from to the real commercial computation, the real commercial quantum computation? Because there are so many excellent simulation work. But for example, for the cloud computation, we can easily apply for Amazon or Huawei cloud computer. Will this same situation happen for the quantum computation? Is it still far away or maybe soon? How do you think about it? Thank you.
I don't know actually. So it's I think nobody knows. So. Or doesn't anybody? I have no comment on that, or I couldn't comment on that actually.
One thing one can say is the following: one thing one can say is what the big companies themselves say, right? One can quote them, like Google claims that they will have 1 million physical qubit quantum computer in 2029, which will be error corrected, and logical qubits, one logical qubit will be based on 1,000 physical qubits. So it would be basically it would be a 1,000 logical qubit quantum computer that you could not, of course, simulate classically. And then, of course, Google also made there was some people from Google, Craig Gidney and others. They calculated how much time it would make them to break up an RSA code that is used today, and they would need 20 million physical qubits, not 1 million. So that's one order of magnitude, or maybe two. Further, so that's what they claim. But if we really will be there in 2029, it's doubtful. Yeah.
Any other question? Not. Thank you again for this nice lecture. This lecturer is Gregory Morse, who are going to talk about custom Taylor FPGA boson sampling.
Edge kicsit. See, like my doodle. This is not mine. Oh, just put it in my pocket. Okay, fair enough. Start. All right. Thank you. Okay. Hello, I'm Gregory Morse from Bush-Laurent University, and I'm giving this presentation about what I'm calling custom-tailored boson sampling, because we're going to kind of elaborate on some of, especially what we saw in Zoltan's talk earlier with the DFE work, the data flow engine. And I do this in collaboration with my supervisor, Tomasz Kozik, and kind of our project supervisor, Peter Raketa. And we're also, giving thanks to the Quantum Information National Laboratory, who we're under, as well as Wigner. And this is kind of a cross collaboration between the ELTA informatics faculty as well as the science faculty. So specifically the physics department. And I, myself and Tomasz Kozik are in the programming languages department. So as kind of has already been said, the permanent of a matrix is one of the key underlying computations that boson sampling that underlies boson sampling effectively, that's needed to actually do the classical simulation. So we took the best formula, which is the Subramanian, Box, Franklin, Glynn formula. If I got that correct, it's it's a long name, but we'll just refer to it as BBFG from here on out. So we use this formula because it has a complexity of n times 2 to the n minus 1, if done with a reflected binary gray code only. Otherwise, it would be n squared. So you actually have to use the gray code to get the kind of the cutting edge state of the art complexity there. There is another formula called riser, and we'll look at that a little bit later. So basically, we took the FPGA and we distributed the work to even kind of further reduce that equation by dividing by 4 effectively. And we also did it with the I think I hit a wrong button here. Okay, so we also did it with the okay, is there a pointer on here? Yeah. Okay, thank you. Yeah. Okay, so we also did it with the dual mode, and basically what you can see here is we have two results actually. The first is that we did it with a just ordinary permanent computation, and we built at 280 megahertz. And the second is that we did it with a repeated variant, which built at 240 megahertz. And we're going to go into this, but in realistic boson sampling, it's not just a permanent, because as we saw in the previous lecture, the Fock state has these multiplicities. There's more than one photon on a mode. So what you really need is you need a repeated row and column permanent, which is a little bit different and it's more specialized. And that's why we call this custom tailored, because it's not just computing a permanent, it's computing a more general version of the permanent. So this is kind of, what a realistic simulation setup may look like. You have your fiber optic cables and you're sending photons through a real simulation with beam splitters and all these different types of gates. And then you have a detector on the output that measures the number of photons. So, okay, so we're going to go a little bit more into this BBFG formula. And this formula is basically the best known one still. There's also the riser formula, and the riser formula can also achieve a similar complexity by doing some really tricky, not very well-known reductions that lead to a very similar looking formula. So effectively, not very different. But this formula requires a lot of sums in here, and that's where the gray code's applied. The gray code's applied so that these summations can not constantly be done. Instead of doing summations from 1 to m, you can just effectively add and subtract very cleverly with the gray code so that you don't have to do all of them. Then you have to do all these products, and there's really not much of a choice there, and those are very expensive. The most expensive, obviously, multiplication. And finally, you have to do a little parity adjustment, and you have to do an outer sum here. So the interferometer matrix, as it's called in a real Boson sampling setup, would be the this matrix A, and a library like Picasso will generate such a matrix. And delta is the binary gray code, and so it's just effectively 1 or -1s stringed along in this context. There's sometimes you can use 1 and 0 in this context, 1 and -1 gray code, but it's the same thing. Obviously, you just interpret -1 or 0 is -1 or something like that. So in general, though, the permanent formula will become a bit more complicated when we try to put repeated rows and repeated columns in it. So if we have these multiplicities where we have certain rows and columns which are 0, there's no photons on them, and there's some with 2 or 3 or however many photons on them, well, you have to restructure the formula a bit. And the interesting thing is that it's no longer as symmetrical. It's no longer a symmetrical formula because here we're going to take it to the power of the column multiplicity, and the row multiplicity is taken into account here where it's doing the summations. And here is the simplification this formula can provide. It uses binomial coefficients, which are multiplied together, to actually reduce the overall complexity. So instead of having to take the same number as this, which would be 2 to the n-1, now instead we can take the multiplication of all the row multiplicities. Okay, so that now this formula does require, of course, that you do have this. This is not trying to be a rectangular permanent in any way. You have to have preservation of your photons. So the same number of row and column multiplicities, which correspond to the rows correspond to the output multiplicities, the number of photons on the output, and the columns are the number on the input. Of course, you can always transpose, but that's usually how it's done, and that's how it's done in Picasso. So the complexity now is just multiplying all the different row multiplicities. If you add 1 to them and just multiply them all together, which can be a major, major reduction. I mean, if you think about it, a 40 by 40 permanent here would be 2 to the power of 39. Whereas if you had just one row multiplicity of 40, now it's going to do whatever 20 a very small amount of computations, 41 computations, I think. But basically, you can see because you're going to just it's a little there is an anchor row, hence the power of 2 to the n-1. So the anchor row needs to be accounted for. But what you can see is that it would be a very, very small number of computations. So this is the generalization of the above formula. And this is what we needed to implement to achieve state-of-the-art and good performance. Okay, so the tool that we're using is the Alveo U250, which is a FPGA card, which is basically one of the best in existence right now. It's got a lot of DSP units, which is somewhere listed, 12,288 DSP slices. And those digital signal processing units are basically multipliers. And they can multiply 18-bit by 25-bit numbers. And that's going to be the premium that we're going to try to distribute all those multiplications over. those digital signal processing units. And there's also a floor plan and some details about this, about how it's arranged into these 4 super logic regions. And this is the structure. And the PCI Express connects down at the bottom here. So we did some things to check after we had some working FPGA results. We wanted to check the accuracy of what we did. And so we implemented a MPFR, which is the multi-precision floating point reliability library, as part of GNU. And we made an infinite precision calculator, which, you know, used with addition and multiplication would constantly be adjusting bit sizes and stuff. And so we did that, and it's now going to be a part of Picasso Boost, the extension to Picasso. We also, for our accuracy, we had to make a trade-off where we could not use the typical 4m+2a complex multiplication, which is what everybody, you know, learns in math class. So where you multiply 2 complex numbers with 4 multiplications and 2 additions, we use Knuth's 3m+5a formula, which can be a little bit less numerically stable, but for our purposes, with normalization, which was used because we're talking about fixed point numbers, when usually it's kind of implied when dealing with an FPGA that generally you will use fixed point numbers, not floating point numbers, not always, but that is what I'm referring to here. And that's why we use this formula, because we needed to cut down on the number of DSP units used. And so this formula also is pretty smooth because you see it's a multiplication with something that's added or subtracted all happening simultaneously. So it pipelines very nicely. So the normalization we used, we had to keep all the values between -1 and 1. So that would mean like 2 integer bits and the rest would be fraction bits. And basically we also had to keep the absolute value that way. For the inner sum, we needed these two, the imaginary and real part. But for the products, we needed the absolute value to be between 1 and -1, so they would always stay normalized. However, despite using some Euclidean vector tricks to actually achieve this, you know, knowing how the things could be added or subtracted in the permanent and trying to figure out how to normalize it perfectly, we eventually did. The outer sum could have partial sums, which could overflow. But then we just add some integer bits. And this formula is just attempting to take the positive and the negative parts of that formula and take the extreme value and dividing by n to the n to account for a simple identity matrix where if you put all ones in there, then the normalization would be 1/n, very simple. And so you can use a couple tricks and you find out that, you know, you need an extra 6 bits. So have to be careful. So the time complexity, as I said at the beginning, it's reduced a little bit differently for single and dual. If we use the dual DFE, we can actually double the speed, of course, because it's basically using 2 FPGA units on 1 PCI Express card. So that picture I showed you before, there are actually 2 FPGAs on the Alveo U250, and you can use them both. So the area is, I mean, it's going to be dominated by the flip-flops where we stored the matrix. For speed, we don't use RAM, we just use flip-flops. And the multiplication tree we kind of alluded to. Here is the different accuracies we ended up even having to use. We start with 64-bit numbers and then we, you know, go to 93 bits, 110 bits. We can't use the full output. Of course, there's going to be limits. We have to keep the number of DSPs down because we could consume easily all of them if we weren't careful with this and using the complex multiplication trick. The design, we split the matrix into quarters and we send each quarter to do its initial column sums and then followed by the initial column sums. Instead of summing initial sums, it would just do the different gray code sums. So the gray code counter would be here, and then it would just go right to product kernels. These are 4 different product kernels, and you can see it has to crisscross all the different parts back together. And then here it just does the final outer sum. Okay. However, when it comes to repeated rows and columns, the situation gets a lot more complicated. Here, we had to come up with using a reflected n-ary gray code. Using a direction encoding to achieve the constant time that we required. So basically the binomial coefficients that I showed in the previous formula, well, you can't just compute binomial coefficients in one tick like you could do with addition. So with the gray code updates, you're doing these one tick operations. You don't need any loops, very smooth on the FPGA. But here we came up with a way of at least not having to do any big computations. So we could take the next binomial coefficient, since we're using a gray code, it's kind of, something like n chooses k times, n chooses k minus 1 type of thing, where you can simplify or divide it by. So you're dividing by the old binomial coefficient and you're multiplying by the new one. But it simplifies into two formulas here. And so you're basically multiplying by numbers up to 40 and dividing by numbers up to 40. And we could use some magic number multiplication tricks and other things to reduce eventually the loop length down to 9. And then we had to stagger the gray codes at these intervals. So since we're dividing, like, for example, this computation with these multiplicities, so I've bold fonted every 2, because this would be the starting points effectively that it would have to use to stagger it. So it would start one computation here, one here. This would only go for effectively two times through the loop, because it would do this one, and then the next time through the loop, the binomial coefficient would be available so that it would have it. And so this is just using some very clever loop tricks on the FPGA, and of course, increasing the initialization time. But it's marginal, so it doesn't really matter. So our results, and this is going to be several different pictures here to deal justice to this. And basically, the first result here is the accuracy. So the accuracy, you can see, holds until about 36 by 36 matrices. Now, this is the normal permanent, not the repeated one. So which is more important in some sense. So for determining initial judgments, because with the repeated ones, you have to account for the different number of photons. And of course, we can use random multinomial distributions to find those, but it's not going to give as consistent results as the normal permanent. So what we can see is we do taper off, but our accuracy does hold quite well. And if we look at a library like the Walrus, one of our kind of competitors that uses the riser formula, we can see that the accuracy with a double floating point type goes way off. And even with a long double, it goes way up here. It's going to be much slower too. And our libraries with C++, we can actually use a double data type and a long double, and we can achieve better than the Walrus can using a gray code strategy. So, and the BBFG formula, of course, which is known, by the way, that the BBFG formula is a bit more numerically stable. So that's one of the reasons why this accuracy situation occurs. Okay, so as far as the performance, there is a couple things we looked at. Mainly, we would look at the difference in time at the very highest size here, so like at 40 by 40 matrices. And we also looked at the crossover threshold, which I've put with these gray lines here. So where does the DFE start to exceed the C++ implementations? And where does it stay basically in that range where it's going to beat the C++ and it doesn't, there's no latency or any other initialization issues later. So at these points around 15, 17 for the dual is actually a slower initialization. It's okay. Okay. Yeah. Is it working? Yes. Okay. Perfect. So, okay, I'm going to continue on here. Sorry about this technical glitch. The speed up here we can see though is very significant depending on what you compare it to. Obviously, we like to compare it to the long double, as the long double is, as we saw before, is much more accurate. Oops, am I on the wrong? Okay. And so, I've managed to go further. So this is the 280 megahertz normal permanent results, and we see the dual, of course, is twice as fast. And here's our DFE, and we can see that yes, the double precision formula comes very close actually on the CPU, but it's much less accurate. So if you want precision, we're still clearly better than this next line of items over here, which is where the long double data type, which is the only one that will really hold precision, would come in. So here, this was, yes, the next slide. This is the batching. So what we did is we used batching so that we could put a bunch of matrices back to back and just stream them all to the FPGA, and it would just return a series of computations using some tricks on the FPGA, so everything automatically resets and it just keeps processing. And with batching, the initialization time starts to drop down, and we can see these two crossover lines have now shifted very far to the left. So now even for 8 or 10 photons, we can be competitive. So this is a key technique on the FPGA. Here for the repeated permanence, here's our results. At 20 photons, which is what you're seeing here, there's a very slight benefit because the initialization time is dominating. You can see we're pretty much at a flat line here because it's dominated by the initialization time. Now let's look at batching. Now with batching, all of a sudden things look a lot better. The initialization time is no longer the big problem here, even with 20 photons. Now the batch size we used is equal to the matrix size used. We were testing up to 0 to 60 by 60 matrices, and it's based on the Clifford and Clifford faster classical boson sampling, motivated from there, because that's how many permanents we can do at one time. And or the algorithm requires us to do it one time. With 30 photons, we can see already the initialization time, even without batching, has changed, and we're just clearly a lot better. And with batching there, still, there are maybe a little bit of some stalling type issues, which has made these speeds not quite as impressive as they were on the prior slide. So there are some technical issues here, because you can see that it's right at 60, it drops down here. And here we don't have quite as sharp a drop down. And the actual reason for this is going to be some kind of very low level technical issue. But in general, the results are still very good. And we can actually, we have less computation formulas to compare against, because the Walrus and other libraries don't implement a special variant of the repeated row column permanent. So some last little things. The upload time is 56.2 seconds and 112 seconds, depending on a single or dual mode for the FPGA. The running time can be computed precisely. So that's kind of nice because we know the actual megahertz that we're running at. So it's a very simple computation to get the same results that we're getting in the pictures. So that's also a nice confirmation. And the if we were to do this with long doubles, this would be operating at 285.5 gigaflops. I know this is kind of a fake measure. We're using, normalized fixed point numbers, but if we did it with long doubles and it was running at this speed, this would be the effective gigaflops that we're achieving. And as far as the power, okay, it's using a little bit of power. Basically, you can do a simple computation there. And we can see here it's using about 14.83 watts. This is an estimate. Of course, none of this is very accurate. We'd need special equipment to measure it. And we don't use that many lookup tables or flip-flops. The DSPs, you can see we got it all the way down to here by using some Karatsuba multiplication and rectangular tiling with these 18 by 25 multiplication units. Very low-level stuff, but also something that the Max compiler, which we used for this, which would not be able to, by its throwing things over to the Xilinx defaults, would never achieve such a low amount of DSPs. It would just be hopeless, basically. It would probably be either, you know, in the high 90% range or even go over 100%. This is the aerial view of what we did. So this is the different kernels here, over here, and there's these streams between the kernels. And there are some issues here, and they're preventing us from going much higher. So if we want to get 300, 320, 350 megahertz, which really did aim for, but these streams are not quite reaching as far as they need to reach. So they're supposed to cross the fabric here. You can see the little boundaries, and they have to have enough registers, and there's just a whole lot of technical details to dealing with this FPGA programming. One of the things I found while doing this is that the VHDL code, which is generated by Max compiler, is simply not low level enough to solve a lot of the issues. And you actually have to go into the Xilinx manuals, start reading about multiplexers and all these kind of very, very technical low-level details if you want to achieve a very high megahertz. So you can achieve a reasonable performance often with these tools, almost for free. But if you really, really want to push the extreme usage of the resources on the FPGA and the megahertz, pumping the frequency up, as close to 500 megahertz as you can get, you will just be overloaded with all sorts of little technical issues, because this physical stuff can get very tricky. So yeah, the conclusion is that the FPGA is competitive, and that the state-of-the-art algorithms can give you a good performance in megahertz on the FPGA too, if you're willing to put the time in and figure that stuff out. Also in the future, we're planning on taking this to the next step, which is to do the loop Hafnian. And we're going to use now the Grok card, which we've received, and we're going to link the Grok card to the FPGA. And so we're going to be able to split the work between the two, because the Grok card might be able to do multiplication, matrix multiplications and things of that nature much more efficiently. And so then we can just stream data back and forth and find a way to do the loop Hafnian computation. So thank you very much.
Thank you very much. So we are 5 minutes delay, so one quick question. Thank you very much.
So this may be one of the dumbest questions, but
no, it's okay.
When you talked about multiplication, like that there are fixed point numbers as much as possible when using an multiplications that you were talking about, and then comparing to C++ long double implementations, whatever. The DSPs, are they doing floating point multiplication or fixed?
Fixed point. They're doing integer multiplications that are 18 by 25 signed integer bits, which means even only 17 by 24 unsigned bits. And so when you're going to deal with the tiling of that, yes. So we've actually already implemented our own floating point multipliers for the long double size. And it actually, it's reduced what Max compiler gives you a 22 tick, or Xilinx, they kind of pass through, down to 7 ticks. So we've dramatically reduced it by using custom tiling. But yeah, at the end of the day, the Grok chip has floating point specific units, but the DSPs on the Alveo are fixed point.
Thank you very much. And our next speaker is Peter Rakita. speak about approximate quantum. Thank you.
Do you hear me? Okay, so where should I put it? Maybe here. Okay, so and this time I will tell you about our work regarding approximate quantum gate synthesis. This work was done by me and with Zoltán Cimborás. And I think we achieved a very good result in this topic. But firstly, I will tell you about something about quantum gate decomposition. What is it? How should you interpret this terminology? Basically, if you have a closed quantum system, it evolves in time according to some unitary time evolution. So this is like an ideal quantum computer. Okay, so basically, if you are programming a quantum computer, you are programming unitary matrices onto it. The question is how to work a quantum processor to execute such a random or general unitary program. And that's the key point, because you need to expand your unitary program into a sequence of smaller unitaries that can be executed on the quantum processor. Okay, these are some elementary operation that can be processed by the quantum computer. So basically, speaking about quantum gate decomposition, it's something like quantum compiling, like you are compiling your C or C++ program. This is also a compiler, just it compiles a quantum program into a sequence of elementary operations. The problem is that if it comes to express a matrix as a sum of other matrices, it's an easy task because we have linear algebra behind it and so on. But express a matrix as a multiplication of many other smaller matrices, that's a very heavy task. It's very difficult to do. Okay, here is a small drawing just to give you some hint about how should be interpreted these small unitaries. Let's say we have 4 quantum bits. You know, each quantum bit can be represented on a block sphere. It can be mapped as the 3-dimensional unit vector on the block sphere. And each of these quantum gates, let's say these purple ones, can make a rotation on these 3-dimensional vectors, and that's one operation. There are other quantum gates that can make entanglement between 2 quantum bits. And the cooperation of these single and 2 qubit gates can be used to express any general n times n unitary. This is a mathematical theorem behind it. You just need to believe me in this. And these black lines are the timelines of the qubits. So we can see that first operation is this 2 qubit CNOT gate. The second one is this U2 and so on. The CNOT gates are controlled CNOT gates, so depending on the state of the control qubit, not operation is made or not made on the target qubit. So this is how you should interpret it. But the question is how to express a quantum program as a product of smaller matrices. Because, you know, the problem is twofold. Firstly, you need to solve some kind of a combinatorial problem of how to place these elementary gates. They cannot be usually they cannot be, they are not commuting with each other. You cannot change the order of the gates. Only if they act on a different qubit, then of course you can exchange them, but in general you can. So you have a combinatorial problem how to place the gates. Then, as I told you, these purple gates are rotational gate in principle, and they can rotate the qubit, the state of the qubit, by a continuous parameter, continuous angle. So they have continuous parameters in themselves. So secondly, you have a problem to find these continuous parameter that describes the unitary program you want to run on the quantum processor. Okay, so one option is to tune these parameters by some optimization algorithm. Find the closest unitary that is the closest to the unitary you want to run on the quantum processor. But how to measure the distance between the exact quantum program you would like to run on the processor and the approximated one you have programmed? And to this, we introduce some simple, very simple definition. Let's say we label the time evolution by unitary U of the initial state vector this way. Okay, just the U acting on the initial state, and the same is done using the approximate unitary we are programming actually on the quantum processor. Then we can define a quantity called fidelity, which computes the overlap between the exact and the approximated time evolution, and you want to achieve as high fidelity as you can, averaging over all the initial states in the Hilbert space. Okay, and it turns out that if you introduce this Hilbert-Schmidt test quantity, then the fidelity can be expressed with this scalar function, which is simple to calculate. Okay, it's nothing difficult to calculate it, because you need to calculate only the product of these two matrices, take the trace, take the square, and some small arithmetic process on that. And if this distance, if the approximate unitary comes very close to the U, then this distance becomes 0 and the fidelity is 1. This is the theoretically maximal fidelity that can be achieved. This is our goal. In some work, another kind of fidelity and distance can be introduced based on the Frobenius norm. This is a simple formula. You see, you just sum up the square of the absolute values of the matrix elements and finally take the square root of it. And it turns out that the distance of these two matrices based on this norm can be calculated even easier than the previous one. Even less arithmetical operation need to be done. And if you define a new fidelity based on this quantity, it can be proved that this new fidelity is less or equal to the previous fidelity. So using this metric to quantify the distance between the two unitaries would be fine. It won't give you a false result. because here you have just a mathematical definition, and here you had some quantum mechanical motivation to introduce this quantity, and this is even easier to calculate. So this is what we used in our calculation to measure the distance between the u and v. Before I tell you about our algorithm, let's talk about our competitors. Basically, we compared our tool, which I will introduce in some of the next slides. We compared it to some state-of-the-art with the most efficient quantum gate decomposers on the field, which is developed by physicists at Berkeley National Laboratory. And there are two tools, the QFAST, Quantum Fast Approximate Synthesis tool, and the so-called QSearch tool that both of them can be used to compile quantum program. And the goal is to compile them with the fewest operation as it is possible. Okay, because today's noisy quantum computers are noisy. Okay, I just tell it. And if you have more operation in it, then the result would be less meaningful. You need to express your quantum program with as few as possible operations. Okay, and we also use the compiler named Qiskit, or implemented in Qiskit, provided by IBM, because this is IBM provides access for quantum computer processor for free. Okay, so this is we needed to include in our benchmarks. Okay, the strategy of the QSearch algorithm is very simple. They basically they do a search over a tree to find the best configuration of the quantum gates. They steps are break down into 2-qubit building blocks. Okay, this is rotation on 1 qubit, rotation on the second, and the 2-qubit gates connecting the 2 qubits. And they are trying to find a solution for the optimization problem by step, adding the next 2-qubit block here on there. Okay, the problem, okay, with this way, they can find the most optimal quantum gate decomposition for sure. Just they need to pay an exponential time for it, because this tree expand exponentially. So they are trying to follow some logic to find the most efficient search path and so on. But the problem is there are no good strategies for that. Okay, so in many cases, this algorithm simply doesn't give you any result in a long time. The second one, the QFAST algorithm, is breaking down the n qubit unitary into a product of n over 2, n over 4 by parameterizing the unitary with this formula, and using this alpha parameter, they can limit these unitaries regarding on what qubit they are acting on. Okay, so again, they are breaking down the problem step by step. Of course, due to this generality, okay, the procedure works very fine. Just due to this generality, they miss the most optimal gate decomposition. The result contains more gates in the resulting quantum circuit, but the algorithm works quite fine and reliably. And this is a scheme of our algorithm. We also use 2-qubit building blocks in our system, and for the 2-qubit gates in this small building block, we use some controlled rotation, because Okay, depending on the state of the control qubit, we perform some rotation on the other qubit. But this rotation can be an identity or some other trivial thing. And if it turns to be an identity, then it can be kicked out from the quantum circle. And this is the way we can start to compress our quantum circuit. And at the end, when we don't find any other building blocks that can be excluded from the quantum circuit, we just convert the controlled rotation gates into a sequence of two C0 gates, or there are some other special case when it can be expressed with 1-2 qubit gates, which can be executed by the quantum processor, of course. Okay, and this way we can sequentially reduce the length or the number of the elements in our quantum circuit. Okay, we make our benchmark on a set of quantum program of 3, 4, and 5 qubit provided by the Qiskit developer challenge. So this is a set that can be accessed by anyone. And we also use in our benchmark some well-known quantum programs, but I don't want to go into details here. Just show you our results on our benchmark. Here are the C0 gate counts. Usually people give you the C0 gate count because the 2 qubit gates are much harder to realize in actual hardware than single qubit gates. So a good measure to tell you how complex is your quantum circuit is to give you the number of the C0 gates. And in the first column, you see the number of initial C0 gates of the program taken from this set, from this database. Okay. Then we use the Qiskit to compile the unitary, and you see that there is a great increase in gate count. Then we use our Squander tool, which implements this algorithm I just told you about, QFast and QSearch. If you compare the C0 gate count, you see that the count provided by our tool is significantly less than the other one. Here the dash means that the QSearch algorithm didn't give us any result in a 24-hour time limit. Only one example is here when these two algorithms seem to work more efficiently. But you see, this is a very extreme example. It's a very simple. Again, some other program, we again see that our Squander package systematically provides significantly fewer gate count in the decomposed or the compiled quantum circuit. But there is one shortcoming, and this is the execution time. If you compare with the execution time of Squander with QFast, you see that Squander is in general 4 or 5 times slower than QFast. This is a price we need to pay, but we are working on it to improve the speed of our compiler. Summarizing our benchmark, we found that in 21% of these quantum programs, we could reduce the gate count compared to the initial gate count by more than 50%, which is a nice thing, because previously people thought that these programs are contains the fewest gate as possible, and we always keep a very high accuracy. The distance between the two programs is less than 10 on the -8. Okay, so I think this is a very nice result. Our tool is accessible on GitHub, and we already have more than 5,000 Git clones from the site. So people are using this tool. Okay, but this comes in an exchange of larger execution time, as I said. So what can we do about it? Firstly, we are about to experiment with first order optimization algorithm in our Squander package. Currently, we are using a second order optimization procedure when we also calculate the curvature of the cost function, which takes much time. Also, we would like to put our computing kernels on FPGA. You know, a quantum compiler is nothing else than a quantum computer simulator, because you need somehow simulate the effect of the quantum program. And there are some, you can introduce some unified computing kernels for the quantum gates. And we are about to implement these computing kernels on FPGA in the future. So this is our next project after finishing the permanent stuff. Okay, finally, I would like to acknowledge some support of Hungarian grants to enable us to work on this very nice project. And if you have some question about our result, not just this quantum gate decomposition, but the FPGA related stuff, then you are free to contact me at this email. So thank you for your attention. That's all from my side.
Thank you very much. Is there any question? Danish, please.
So if I look at your results, on there was this Q-search and the Q-fast comparison. So you had a line, like I think 6 from top, where actually you are more optimal than even Q-search. So Q-search cannot find the optimal solution.
This is a Q-search, all right?
Exactly. And you have 13 there. So you have in line 6.
Yes,
13,
because
and you have
Q-search, no, okay, they need to introduce some strategy how they walk through the tree. And the strategy might exclude the most optimal gate decomposition. They just find a less optimal decomposition sooner. That's the thing behind it.
Thanks.
Other question?
I'm wondering if there's any parallels between this and Boolean logic circuit optimization. Like that, I know it's an NP hard problem to do, but of course that means you can't have any approximation. There's no room for approximation. But here, is there a way to do a perfect no approximation strategy, and is there a complexity?
They are working on that. There are some scientific results about that, but I would say that they are the story of the future. If you would have ideal quantum computer for noisy quantum computers, if you have a good approximation for your quantum program, even with less operation, with that discrete set of gates, it's much better.
Thank you very much again for this nice lecture, and let's start with the coffee break. It's 20 minutes, right? Let's begin the next session. Our next speaker is Gábor Bíró from the Vignet, who are speak about optimization with machine learning techniques. Thank you.
Thank you very much. Hi, everyone. I'm Gábor Bíró from the Vignet Research Center for Physics. And my topic will be a little bit changed compared to the ones that we have heard before. So I'm going to talk about some high energy physics applications of some machine learning techniques that we are working on together with Gergely Barnaföldi and with Bence Tankó Bartalis, who is a young student currently studying at the Oxford University. And he will join us also this summer for a summer internship in a few weeks, hopefully. So this is my short outline. I very briefly show you a quick motivation for the machine learning techniques in general. I will view our research goals and finally the results and some future directions. So I think that most of you are aware of why machine learning techniques are good. So take, for example, the Large Hadron Collider data that has been produced so far. It is slightly more than 300 petabytes. And now that the LHC has been restarted just recently, from now on, we will gather more than 200 petabytes every single year. And this number will increase in a very, this number will increase very rapidly from now on. And you have a lot of challenges regarding this. So first you have to store this amount of data. You have to distribute this amount of data all around the world with high-speed internet connection. And of course, you have to process this amount of data. And not just process this amount of data, but you also would like to do some simulations, Monte Carlo event generators, for example. And it is a very, very big challenge because even just 1 second of the LHC data for modern powerful computer, you will need hours, days, or even weeks to simulate. And I really like this picture that shows that how rapidly our technology evolves. So these several tons of data storage could contain 5 megabytes 50 years ago, roughly. And now you can hold even a terabyte just in this size of storage. So this is a huge challenge. You have to process a very large amount of data, but this is the field where you can really use machine learning techniques, where they can be very powerful. So I tried to compress everything, all of the basic building blocks of machine learning on one slide. So machine learning is basically nothing else, just linear algebraic operations repeated after each other. During the consecutive layers, you can do some matrix operations, but what makes it very special are these nonlinear activation functions, which gives the machine learning algorithms the power to predict and analyze the data in a very efficient and powerful way. And basically, there is no one recipe that you can apply for each problem. There are basically infinite number of possible machine learning algorithms. Here, I just listed some basic loss functions and optimizers that you can use out of the box, for example, with the Keras API, but you can implement everything according to your needs, basically. So this is a very, very simple example for a fully connected neural network. Let's say you want to determine that on the picture there is a cat or a dog. And so this is a very simple classification problem. You propagate your picture through your network, and at the end, you will receive a number which gives the probability that what can you see on the picture. And here we can apply, for example, this Huber type of loss function, which is actually not the best choice for classification problems, but here, why not? And you would like to train your network to optimize these weights with the process that's so-called backpropagation, which will update the weights according to the partial derivatives of the loss function. So during the training epochs, you optimize your network to give better and better predictions for the given input. And actually, with very small changes, you can use this kind of simple networks, for example, to determine the centrality of a heavy ion collision, which has been actually done already back in 1996. Here you can see the citation for this paper, where they used such a simple network to determine the centrality, which can be also used today for the high energy heavy ion collision experiments. So I just summarized quickly that there are many, many different types of popular networks with trainable parameters ranging from a few hundred thousands up to even a few hundred billions. For example, Google has some language processing network with few hundred billion of trainable parameters. So basically there is no upper limit for that. And there are infinite amount of possible applications ranging from regression problems or autonomous vehicles or point cloud segmentations, decision trees, transformers. So you can use such networks for anything, basically. But what I would like to highlight here is the high energy physics applications. So in this repository, all of the publications are collected that has something to do with high energy physics. And I really like to update these numbers to demonstrate that how quickly evolving this area is, so how dynamically, how rapidly increasing this number of high energy physics publications with machine learning. So I will not go deep. So I will just list here that some basic applications. You can use machine learning for track reconstruction, which is a very demanding task computationally in high energy physics. You can use neural networks for separating quark and gluon jets, or you can reconstruct the jets themselves with neural networks. You can use them also for tuning Monte Carlo event generators that also Balázs Majoros was talking about yesterday. Or you can use them to fast simulate the detector responses that will speed up your detector calculations. But our goal is to study the parton shower and the hadronization process itself. So here on this cartoon, you can see the well-known schematics of a single proton-proton collision that itself has it is a very complex process. It has several sub-processes like the hard scattering, the parton showers. You can calculate the underlying events, and at the end of the day, you have to do some calculations with the hadronization, during which the color charged partons will confine into the hadrons like pions, kaons, and protons that you will eventually detect with the detectors. So each of these processes can be modeled in several ways, but I want to focus on the hadronization itself, which is traditionally a non-perturbative process that has to be approximated somehow because it cannot be calculated with the traditional perturbative methods. So you have to do some so you have to make some approximations for the hadronization. A very widely used model for the hadronization is the so-called string fragmentation, mainly developed by the Lund University. And we would like to study this specific model of the hadronization. So the main inspiration for our study was given by this very nice paper. Professor Monk was studying the parton shower processes with a very cleverly designed autoencoder type of neural network with only 100 of trainable parameters. And with such a simple network, he was able to reproduce some important high energy physics observable quantities with a good precision. So based on his ideas, we wanted to study the hadronization, as I said. So we wanted to create a neural network that kind of able to mimic the hadronization with in a way that it can convert the parton level observables into hadron level observables, like these pictures. The event display in the rapidity azimuth angle plane. We wanted first to create a network that can create a hadron picture from this to this. Some small remarks regarding the machine learning techniques. So machine learning is a very great tool, and once if you learn it, you will use it like a hammer and you will search for nails everywhere. So it's a very great tool. But actually, if you will use machine learning more and more, you will realize that it is a very, very great tool. And you have to be careful actually with this, because machine learning is only useful if you can actually learn something useful from it, if you can optimize your problem further. So at the very beginning of our study, we actually found many different ways how not to simplify, but over complicate our problems. So this is my message, that you have to be careful and you have to find some very useful purpose for your machine learning tool. So this is what we actually did. We widely used the PITIA Monte Carlo event generator to simulate proton-proton collisions. We filtered the events to have at least 2 energetic jets, and we collected such events. We collected more than 100,000 of such events. From the parton level state, we discretized all of the particles, and basically we saved all of the kinematics into such a, let's say, multicolor picture. And as an output, we took the hadron level and we saved some of the important observables like multiplicities and even shape variables like sphericity. And we saved also the jet transverse momentum, the jet mass, jet width, and jet multiplicity. So that is our input, and that is our output for the machine learning. For the model, we used the very popular ResNet type of architecture, which consists of such skip connections, and that makes it a very robust type of architecture. With that, you can implement very deep architectures that can perform with a high performance. So we tested 2 models with different complexities. The smaller one had slightly more than 1 million trainable parameters, and the bigger, more complex model had almost 2 million trainable parameters. And of course, all of these studies were done with the support of the Wigner Scientific Computational Laboratory, formerly known as the GPU laboratory. So these are the two models that we tested, and let's see the results. So here you can see the main observables. The red dots on these plots are the reference PTA results. The blue dots are for the smaller model, and the green dots are the predictions for the larger, more complex model with more trainable parameters. And what you can see here for the multiplicities, the sphericities, the jet multiplicity, jet width, the jet mass, and the jet transverse momentum. And you can see that both models were able to predict the 7 TeV proton-proton collision results with a high accuracy, but actually the more complex, larger model marked with the green, it was able to reproduce the results with a higher precision. So I want to emphasize here that, of course, the validation was performed with a separate data set generated just for the validation purposes that was not included during the training. Okay, so these results are nice, but as I said, is it really useful? So can we learn something with this network? So we checked that how the multiplicity scales with the collision energies that was not included in the training in any way. So here you can see the multiplicity density in the function of the collision energy. This was our training energy, and we investigated the predicted multiplicity in lower and higher energies. And here you can see that it scales very, very nicely. So our networks were actually able to learn something about multiplicity scaling. And you can see some similar plots here, but here we almost doubled the collision energy for 13 TeV. And again, you can see that there are some discrepancies, but in general, the shapes and the expected values are very reproduced in a high precision for both of the networks. So these were our main results, but the question arises that can we do something more effective? Because if, as I said earlier, we basically discretized everything, each of the kinematics into this plane, but it is a very ineffective way, because if you think about it, roughly the 80–90% of these pixels will be actually empty. There will be nothing in that. So we want to somehow filter the pixels that contains more information, and we will try to use this method called singular value decomposition, which says that every matrix can be decomposed in a very clever way, which has the very nice features that it can be ordered by importance, and it is guaranteed to exist uniquely, which means that you can decompose your original matrix, which, let's say, this particle level information, in a more compressed way, and you can reduce the dimensionality of your input with orders of magnitude. So using this decomposition, we made some preliminary results that could process with the neural networks with a more effective way, and these are the very first preliminary results with some correlation plots for the jet observables, and here you can see that it works actually very, very nicely. So these are just the very first results. More will come very soon, so stay tuned. And here you can see my summary. So we are using machine learning methods to investigate high energy physics applications, specifically the hadronization process. And it has very interesting future prospects, like this dimensional reduction that I was just talking about. But it is a very interesting question that can we scale up the faulting for heavy ion collisions, for example? And what happens if we want to investigate some centrality dependent quantities like collective effects, for example, the transverse flow or jet quenching or anything like that. So hopefully these results will come very soon. And thank you for the support for our grants, and thank you for your attention.
Any question?
May I ask some details about what you said in the your last transparency and the singular value decomposition? That this matrix is the picture of the two-dimensional input picture.
In this case, yes.
Yes. So and you use this singular value decomposition and use only the singular values in from it, or use somehow the eigenvectors, so to say.
Well, we are in the very beginning phase of this study, but we are using I think some Python package to compute these matrices, and with some arbitrary chosen limit of this R, we cut this series. So we use only the first, I don't remember the first R members of this series, which will reduce this amount of number into this that in principle contains the most important information.
Thank you.
Any more questions? If it's not, thank you for your lecture.
Thank you.
And our next speaker is Ágoston Kaposi.
Okay. Hello, everyone. I am Ágoston Kaposi. I am a PhD student at the Eötvös Loránd University. My topic will be jumping back to the first session. So I will talk about quantum computing results, which we achieved in a cooperation with Péter Rakita, Zimboraj Zoltán, Zoltán Kolarowski, and Tamás Kozsik. And yes, so just to remind everybody that how we or what kind of quantum computation we do. It's the photonic one when we have Q modes, and I will just try to explain you how I look at it. So I just look at this computer that we will have some light sources or particle sources in the beginning and some particle detectors at the end, and that's the main part of it, but I cannot understand, or because it's physically not so easily doable. And even the main thing, which is between these layers, is also very hard. So this is something which I look at how I learned that the physics subject in high school studies, that some magic happens with the light sources or with the particles, that they interfere and so on. Something magic happens there, and yeah. So even if we just look at a simple thing that we want to here just fire two photons in two different modes at the same time, but exactly at the same time, it's very, very hard physically. So because of this and because of these limitations, we have to restrict ourselves that we don't consider the general cases. And now I want to talk about the Gaussian states. That so they are just the states which are which can be achieved via some gates, like it was before, and they have the property that they have at most quadratic Hamiltonian, and then we can perform just linear gates on it, and so these are the beam splitters and squeezing and displacement gates which we can use, and so on. There are some others, but these are the main ones which we can use. And the Gaussian state can be fully characterized by their mean vector and the covariance matrix. And this means that we can store it in our simulator more efficiently than the Fock base and the Fock states, which we had other talks about. And I want to show you a little bit of practical things, which is the reduction, that we can have a matrix of any size and another vector from 0, 1 numbers, and we will reduce the matrix based on this vector, which means that we will throw out the rows and columns corresponding to the zeros. So here you can see that the 0 means that the first row and column is thrown out, and the third as well. So we will have a 2 by 2 matrix in the end. And in our case, as I showed it already, that we have these 2n. So the multiplicity or the dimension of our spaces are 2n, which means that if we have n Q modes, these big N Q modes, then we will have the matrices of size 2n by 2n, and that means that we will have block reductions at our cases. Okay, that means that we can see the matrix like 2 by 2 block matrix, and then we will reduce each blocks by the S, so it can be described by the reduction of S next to an S. And we will also limit our detectors, because a general detector is not so easy to build physically, and also what in the first talk was mentioned, that a Chinese group showed the quantum supremacy with photonic quantum computers, and they used threshold detectors. And I will also restrict our detectors to this type of detectors, that they can just measure if there was a photon on that Q mode or not. So that's a hard or a big restriction, that we don't measure the photon number or anything like this. We just measure the existence of any photons there. Okay, and then 0 will mean that there were no photons there, and 1 will mean that there was detection. And as I mentioned, these states can be described by the covariance matrix. There are different definitions for the covariance matrices, and here you have to do some technical details on it, but let us just see this big sigma covariance matrix, which is called Fushimi covariance matrix, and we can just add this identity over to the other complex covariance matrix, and we can construct it. And from this sigma, big sigma, we can calculate the exact probability of of a measurement or a possible outcome like this. So if we want to have the exact probability of 0, 1, 0, 1, that's our S, then we can calculate this probability that we will measure this vector with this fraction, which contains this Torontonian, which was already mentioned before, and the determinant. So the determinant is, as we discussed, it can be calculated easily, but the Torontonian is not. So that was also mentioned already, that all in our cases we will have exponential time to simulate the quantum circuit, and the Torontonian is also an exponential, or the Torontonian, to calculate the Torontonian, we also need exponential time. But next to the exponential part in the complexity, we always have something other. And here I want to show a small trick, where with this trick we achieved a speed up in not the exponential factor, in the polynomial factor of the complexity. And to describe this small trick, I will just show you the Torontonian's definition. So it's like not so hard just to understand or just to implement. It's also not so hard, but here we have the summation over all z subsets of these n numbers, and this means that we will have the exponential many summands, and we can see that always if we have this z or z, then we will create a matrix from it, and then we calculate the determinant of this matrix. And if we want to calculate the determinant of a matrix, we can see that that's I don't know, n to the power of omega, and then the omega is something like 2.73 or something like this at general, and also at Hermitian cases. And that means that our Torontonian function could have the complexity, this n to the power of omega times 2 to the n. And if I suppose that the omega is, I don't know, 2, just say 2, then it's then we will show that these omega can be reduced by almost half of it, so it's by 2. Yes, here I have to mention that we always have Hermitian matrices. So these will have real eigenvalues, and it can be calculated a bit easier than a general matrix. So this determinant of a Hermitian matrix, and it's so our solution is based on the Cholesky decomposition or Cholesky decomposition, and there we want to decompose our matrix into the multiplication of two matrices, where one is lower triangular and the other is upper triangular, and this is the LU decomposition, which is also known. But in Hermitian cases, we can suppose that the U is the adjungate of the L, the matrix L, and if we see if we look at the Cholesky decomposition, how we can calculate it, we can see that the elements of this lower triangular matrix is always depending on the left elements from it and the upper part of the matrix. So it's always just if you just take one element, then it will depend on the left top from the matrix from this element. And this was the idea, that then if I can use this information, that it just depends on that part or those other elements, then perhaps if we just do a reduction, then we can use this property. And if we see the Cholesky, again, in this Cholesky decomposition, then we can see that even if I take a whole block, then the top left block depends only on the top left of the original matrix, and these others, so the bottom left, is depending on the already calculated top left one and the original one, so the same at the same place, and then this bottom right also depends on the previous calculated ones and the original one. So it's something what we could use. And if we see a reduction, which is sorry, perhaps I skipped it, that this Z means here a reduction, and that's because it is important. What happens if we do a reduction? So if we do a reduction on our original matrix, then it's also a reduction on the calculated one, and we know what is modified or what was modified, and just the bottom or the lower part of the matrix, which was below these lines, which were eliminated, are modified. So they have to be updated, and not the A11 or L11 doesn't have to be calculated again. Okay, and that's the thing that we can use. And here we gave a recursive algorithm to calculate this Torontonian function, which is just a wise strategy to order these Z's, like it was mentioned before. Then we can reuse the already calculated data. And that's the reason behind our algorithm, that it will be faster than the I don't know, general one or simpler one. And so it is very hard to calculate what is the complexity of this algorithm, because it always reuses data and then just calculates something from it. And then what we do, or what we did, was that we calculated the flops, which the floating point operations, also for the simple case. So when we just do a normal decomposition or Cholesky decomposition for all Z's, and even if we do our more clever one, and we know that this algorithm will be this linear in this log n, and then we could just fit a linear line on the results, and then we could see that that this omega is 1.06. So that means that so from 2.73 we could jump to 1.0069. Okay, so that's a huge speed up. And yes, it's also so the standard algorithm was this had this complexity which scaled with but at the polynomial part is 2.73, and the recursive one was 1.069, and that was this n to the power of 1.666 was the polynomial speed up of our algorithm. We also checked the fidelity of our calculation, because number stability of the calculation is very important, and we compared our algorithm to the state-of-the-art de Varus calculation, which so the Xanadu company, they developed this Torontonian function, and they have so just only they have similar or any calculation of the Torontonian function, so we could compare our results to them, and we could see that we could do the double precision and the extended precision, so long double precision to the so we have both implementation for the Torontonian, the recursive Torontonian, and we could see that the precision was also almost the same. So it's at double precision we could not jump so very high. And here I have to mention that the Toronto, so the Varus, which is the strawberry, so the part of the strawberry fields, which is the C++ version of it. So they use extended precision always. So we could just compare to that level. And yes, so yeah. And about the runtimes, so we could plot the runtime of the Varus, which is also C++ code, and we could compile our algorithm with the same compiler and on the same machine as the Varus was compiled, and then we could compare our two algorithms. So that meant about 233.7-fold speed up in the runtime. So that's a huge speed up. And even if you see that this 10 to the power of 4, it is not the time I want to wait for one result. And here I want to mention it again that this is the exact calculation of the Torontonian. And there are several other algorithms to give us a threshold measurement. So not just that way, but the exact calculation is just this. So the Torontonian function. So there are another method which can be used where the exponential factor was reduced. So there is a paper about that, but it's, from last summer. But that's not an exact calculation of the Torontonian. And that was my talk. So thank you for your attention.
Thank you very much. Is there any question?
So you said you only wanted to compute the exponent numerically, but of course it's not that satisfying, am I right? So at least an upper bound on what it is with your new method. I mean, what if n is 1,000,000, am I right? So there has to be some way to at least estimate an upper bound and demonstrate in the upper bound that your thing is actually fast.
I don't know what we could do exactly, but I would say that we cannot be slower. That's for sure. But exactly calculate the exponent or the exponential factor.
So an upper bound which is lower than the exponent for the normal technique, and that would be enough as long as it's smaller than the one in the normal technique.
Yeah, I was actually kind of on the same topic, and I'm wondering if, since you said you used flops, were you considering, since there's both additions and multiplications in your formula, and they have potentially, can you just treat that as a constant like that?
So we just looked at the, I think that was with different weights. So when we summed up the floating point operation, so if we just multiplied, then I don't know, that was 2 times the addition, or I don't know exactly the coefficients. So that was calculated that way.
My question would be that you mentioned that the Varus uses extended precision. You use also double precision, and you can use an approximate solution or determination of the matrix. In practice, what is the accuracy that you need?
I think it's lower than these. So I cannot say the exact accuracy we need, but I would say that these 10 to the minus 10 is enough. And we always had to check so how much precision we need. And you know that this will be different at a big matrix and for the small matrix. So for small cases, perhaps the float precision is also enough. And that was our decision, that we also wanted to check if the double and so the other precisions are how exact or how precise they are. So it was just it was just interesting for us, and just to see the difference between the implementations, because we have to calculate, or we need more capacities to calculate with higher precisions.
Figure. And those S parameters, is a parameter of the quotient state. And you see that depending on that S parameter, the fidelity of the Torontonian function is changing. So there are some cases when even a double precision is enough, but at other, this is called skewness parameter or something like that. At some other skewness parameter, you need extended precision to get an equivalent precision. And you need precision because you are calculating probabilities from it, which need to sum up to unity. And of course, if you are saying that you have an exact simulator of that quantum mechanical process, you need to make a point that below that accuracy, it's not exact simulation, above it is, and so on. So it's up to you to choose, but that probabilities need to sum up to unity, and that's a trick.
Thank you for the nice lecture and for the questions. And our next speaker is Liu, who is talking about machine learning and untitled spectroscopy and lattice QCD.
Okay. Hello everyone, I'm Fei Liu. I'm a PhD student from Snowland Adjacent and also Central China Normal University. Today my topic is about machine learning hydrostatic function in lattice QCD. Okay, at first I would like to introduce our partner institute, Nuclear Science Computing Center at Central China Normal University. Also, we call it NSC3 or NSC cubed. N for nuclear, S for size, C cubed for color 3, also for QCD and high energy physics. It has been built in 2018, and it's mainly for the calculation for the high energy physics. The theoretical peak of this center is about 2.7 pentaflow per second, and the GPU cluster contains 306 NVIDIA V100 plus the 30 A100 GPUs. And as a GPU center for the QCD, it has a good behavior in the world ranking. one of which popular cooperated research with Alta is the machine learning hydrostack function in lattice QCD is today's my topic. Okay, before I show the detail of our model, okay. Let me first to talk about the hydrostack function. The hydrostack function is the most important quantity in lattice simulation. It contains all information about hydrons. We can know more from it about the quark dissociation temperature and having quark diffusion coefficient. However, the hydrostack function cannot directly calculate it from lattice simulation, but what we can get from the lattice is the correlation function. Sorry, what's wrong? Okay, sorry, thank you. What we can get from that is the correlation function. You can see in the relation between the correlation function and the spectral function is here. It's clearly it's an inverse problem that from the creator to reconstruct the spectral function. On the other hand, the correlation function is about the order of 10 data point, but the spectral function is about data of 1,000 or even more data point. The limited information of the correlation function is not enough to reconstruct a smooth spectral function. So it's also an inverse problem. It's also a equals problem. Sorry. The normal method to calculate the spectral function is the max entropy method and the stochastic approach. Sorry, there's something wrong with my slide. Yes. Is there something here? I'm not sure. Okay. Okay. All right. Okay. I'm not sure if you know what is the variation or the encode. Okay, let me introduce. Even we don't have some figures. The variation encode is a method that can be a lateral tool to tackle the inverse problem. From the it has two parts: the encoder and the decoder. We can use the encoder to compromise the input data to the Latin code, and use the decoder to extract the input data. So after training has been done, the decode can be a generative process. To extract the input even without the training set. So it means we can use the decode to extract our spectral function if we have some good constraints on the latent code. So our goal find a certain constraints on the latent space C and design a neural network that can learn to balance the priori and the likelihood of the network. Train the network use a general input. Okay, to achieve our purpose, let me introduce a newly structure of VAE. To reconstruct the spectral function rho from the correlator G, let's start with the conditional probability rho given G. To handle it easily, we use the logarithm term. From the first line, we introduce additional variable Z as a latent code. And from the second line, we also introduce the rho GT and the GGT as the ground truth information as the expectation. And by the definition of Janssen's inequality, we can get the lower boundary of this conditional probability so that we can define a loss function with a lective side of the evidence low boundary. And by the definition of the KL divergence, this loss function can be divided into two parts. The KL divergence gives the difference between these two probabilities. And about the first part, the expectation, we decompose the probability into three parts: the priori information, likelihood, and the evidence. For more details, the priori information contains the Shannon Enos entropy term, which have the ground truth here. I mentioned before is rho GT is from the maximum entropy method. People is miss something here. Sorry, I need to talk it. And the likelihood is also from the maximum entropy method, and the G is a noisy correlator, and the G hat is computed from the rho Z in the latent code. And the weight alpha Z controls the relative weight of the entropy and also the likelihood. Okay, here is the Wall topology of the SVAE. On the training process, we input the ground truth correlator and the ground truth the spectral function to the encode to get the latent code Z. And then from the decode, we can get the spectral function and the weight alpha to find the first term of the loss function. And about the encode 2, we need a noisy Z. Okay, it's still missing something here. Noisy Z, the G is something with some arrows from sample from the Gaussian distribution of the ground truth GT. Combining the encode 1 and encode 2, we can calculate the KL divergence, and it's the second term of the loss function. Then repeat to fit those things simulatively. We can train it. Okay, it's 0 something. Here the training epoch is about 5 million. For reconstruction, because we know nothing about the ground truth in real physics, so we throw away the encode 1, only keep the encode 2, and associate with the decode for the reconstruction. The other important thing is the mock data for training, because we know nothing about the ground truth information, so the mock data should be as generative as possible. Here we give some Gaussian term to simulate some peak here, and in the other is the continuous part. The MI is the fixed location, and here the gamma is the width of the Gaussian part, and the C node is from 0 to 1. And here we use some step function to connect all the things, and those parameters of the step function is from some physical range. Sorry, it's also missing something here. To make it clearly, I plot 5 different mock data randomly here. You can see have some peak structure and continual part. Okay. For the mock test 1, we use the most simple cases only with the continuous part and resonant part. Here, the blue dashed line is the input mock data, and the DM is for the MEM and then the maximum entropy method. Because the maximum entropy method is dependent on the default model. Here we use the best result, the relative best result of the maximum entropy. So there's still something missing here. The blue line is the result of the maximum entropy, and our SVE result is a red line with a band. Okay, you can see both output of spec function from the SVE and MEM can more or less reproduce the input. For more general, we use a model with a resonant peak and a continuous part. From bottom to top, the location of the peak become larger and larger, and from left to right, the width of the peak become larger and large. This range choose based on the charm quark. It can cover all the information of the charm quark. Okay, it's still missing something. You can see at some narrow peak, it can the spec function, maximum method and the SVE method both cannot reconstruct the input model as well, but they have a good the peak location. here, and you can see. But from left to right, you can see the results become better and better. So we can know the reconstruct quality depends on more on the peak wise than the location of the peak. Here is a special model, no relativistic QCD. You can see in the input mock data, the peak is very plain, and a continuous peak. The continuous part is with the resonant peak. The dashed line is the result of MEM. You can see in the MEM peak is too high. And the SVAE result is close to the input mock data, but it still cannot reconstruct the peak location as well. So both the SVAE and MEM cannot reproduce the input QCD spec function in a satisfactory way. Now let's turn to the real lattice data. The application to the Chamonia correlator in the positive scalar channel. This correlator computer on the finding is the lattice from 128 cubed times the 19.8 and 19.6 and 14.8 n tau with a fixed scale approach. Sorry, I'm missing something. you can see here the MEM result is very high, and the SVE result is quite lower, but the peak location is close. It means that both the MEM and the SVE can reconstruct the peak location as well, but not the peak height. But from n tau x to 14.8, you can see by the different default models, the peak location and the height become close, and one of the SVE result is close to one of the MEM result. This means that also the MEM result and the SVE cannot reproduce this peak as well. Okay, still missing something, but I can explain it. Here we also care about the n tau dependence. We can reconstruct the n tau equals to 14.8 from the n tau equals to 19.6 with the same time ratio according to some formula here. Sorry, it's missing. Here we can see the result is highly dependent on the n tau effect. You can see the n tau equals to 14.8 and n tau equals to 14.8 have the close result, but the n tau equals to 19.6 and n tau equals to 19.6 have a very different result. Okay, here is a summary. For summary, we propose a neural network SVE, which can be trained to obtain the most popular image spectral function. And then we will also introduce the training process of the SVE, and for the reconstruction process, we can throw away the encode one of the SVE. And the mock test show, the mock test show that the SVE is comparable to the MEM and even output performance MEM in certain cases. And for the application to the lattice QCD data of the Covariance correlator in the pursuit channel SVE is consistent with the MEM result. And here is one is the all of the MEM and the SVE result have highly n tau dependence. For the outlook, we also use a different kernel. Sorry, it still means something. The kernel in the spectral function to reconstruct those things. Okay. Sorry, it's missing a lot of things in the PDF. That's all. Thank you very much.
Thank you very much. Is there any question in Danish?
Can you go back to the mark data somewhere, 10 slides back or 5 or whatever it was? Oh, this sorry. One more front, the forward direction. No, the other direction. This, exactly. So what I don't understand is, so what are the errors shown here? Like, for example, on the bottom left, I completely missed my peak, bottom left. So 3 rows down, 3 rows down, the bottom line on the left side. Like, both models completely missed my peak, but in the errors shown, it's not somehow reflected. So what one would have expected is that maybe this is a hard problem. So with the input data, there are a lot of other spectral functions which within errors would match, but somehow then you would expect these lines to be much thicker to reflect that. But still, the lines are very thin and they completely miss the peak. So how's the error calculated?
The error is calculated from the jackknife method. Okay, we have 2 ways to calculate. Maybe I show it here in the back line. Maybe not.
Probably the details are not super important as much as, so something is not captured by the error. Somehow the error seems too optimistic.
Yes, yes, yes. I see. At first, we use the jackknife to calculate this error, but we also submit this paper, and the referee told us something wrong with the calculation of the error. Then we change it to the bootstrap. Do you know bootstrap? Yes, here is the bootstrap error. So the error is very small, but if we use the jackknife, the error will be very large and large.
I was probably
Doing?
So in the maximum entropy method, you apply you add the Shannon entropy to the loss function with some coefficients. What is in your case the value of this coefficient, and in this variation autoencoder, do you need at all this thing, or it is implemented in the hardware?
For the Shannon entropy, here we need to provide the ground truth. You see, there's for the training process, there's nothing about the ground truth. If we throw away those Shannon entropy.
But you add the Shannon-James entropy with some coefficient to the loss function.
Here or here?
Yes.
I'm not sure.
One line above, I think. Okay.
So
yeah,
here?
that's right. The coefficients of the two terms are not fixed to one. Actually, it can be different, but usually, referring to the previous question, that usually the missing peak can be the reason or the consequence of choosing the Shannon entropy coefficient too large. And if you decrease its value, sometimes it brings back the peaky structure.
Okay. Here, you see here is something some alpha here. Alpha
yeah, that's right.
Is to control the weight of entropy, and also control is automatically learned by the network. So it can adjust the peak. It cannot be too high.
Thank you very much. And our next lecturer will be Ákos Gellért, who are going to give a lecture about SARS-CoV.
It's okay. Can you hear me? Let's saving to PDF. Yes. Oh, go by. Okay. Welcome, everybody. This is the last talk. Okay. Okay, this is the last talk before lunch. So I promise that this presentation won't so long, and I also promise that I won't show any formulas. And and before I start, this is the first time I'm here, and I would like to talk about this project and the members of this project. So the boss is Professor István Csabai. I think almost everybody knows him in this group, and he's a work package leader at in a Horizon 2020 project. The acronym is VEO, which is the Versatile Emerging Disease Observatory. It's an international project, and this project was an additional work packages were added to this big consortium. So additional financial resource can be used for COVID research. And I joined to this group at the end of the last summer. So I like to tell a few words about the project team members. So Oskilim, he's a PhD student at István Csabai's group, and he has a, I think, MSc degree from Oxford in molecular biology, but he started to learn and do machine learning in the István's group. And Anikó Mentes, she's a biologist. She is a postdoc, and he has a great experience in bioinformatics and big data handling. And Balázs Pál, he's here in this room. He is helping continuously me to solve the IT problems when I try to use the GPU resources of the Wigner Research Institute. And István Csabai was a team leader and scientific think tank of our group. And a few words about me. Basically, I'm a chemist, and I have a PhD degree from structure biology, structure chemistry. And I'm doing the AlphaFold running and data analysis in this project. And as I skimmed through the agenda of this GPU-D and from the last year, I realized that only one presentation was about the structural biology era and topics. I know Tamás Hegedűs very well, and I'm the second one. So I would like to talk about a few words about AlphaFold architecture, because that's why I'm here. We use GPUs to run protein structure prediction and generate thousands of protein structures. So the first, I think almost everyone saw this figure. I'm pretty sure that Tamás also presented this slide. This is from last year paper. So this is a very new technique in protein structure prediction. The first block runs in CPUs yet, and where the query sequence amino acid sequence run against a huge structure database to find hits. And after this step, and this is the most time-consuming step because it requires huge amount of hard disk accession time and events. And the second part is the running on GPUs. In this part, the first block where the magic is happening. I'm not mathematician, but this is the unique why it is. This is why it's so unique among protein structure prediction techniques, because the in this block proteins are not handled as protein models in X, epsilon, Z coordinates. They try to solve a graph interference problem to predict protein structures. And after this block, they use the canonical, so-called canonical molecular mechanical using force fields to generate 3D physical protein models. And this process is repeated 3 times. And at the end, we got very good quality protein models. And the second method, what we want to talk about and what we use the in silico version of this experiment. This is the so-called deep mutational scanning method. This is the results of Tyler Starr and Jesse Bloom's from Jesse Bloom's lab from Washington. They are the best in the world in this topic, and this is the receptor binding domain of the spike protein of the SARS-CoV-2 spike protein, and this is the ACE2 receptor where the coronavirus binds, and this is a X-ray structure. So its three-dimensional structure was determined by experimentally, and these research group do that and this receptor binding domain consists of 201 amino acids only. This is the green part, and there are 20 essential amino acids, and if you want to create a single mutant library of this domain, you have to generate 201 multiplied by 19. This is equal to 3,819 structures, and they do this experimentally in ear cells, and they could measure the binding affinity for all of the single mutants. And these affinity data will be used for machine learning. This is just an ongoing project now. So what we do until this is the as you saw the previous slide. This is the RBD domain in surface representation. This is AC2 receptor, and if we calculate the electrostatic potential of all protein structures using the Poisson-Boltzmann equation, we can use it very fast now. And a step forward, you can see here is the protein-protein interaction interface, and I turn it from 90 degrees. You can see here is a shape and specific shape and specific electrostatic patterns. This is the original Wuhan variant RBD, and why we use the AlphaFold to generate single mutants, because it's very fast, and we can do for a spike protein receptor binding variant to generate the whole single mutants library almost within a week, or it depends on the technical issues anyway. But my colleague Oz will try a machine learning approach to correlate these binding interface fingerprints to the experimental determined affinity values. So as I mentioned, we have multiple aims. The first is single mutant structure database generation for those variants which has experimental data. And as far as I know, the Jesse Bloom's lab already done the alpha, beta, delta, eta, and the Omicron variants deep mutation scanning experiments, and we can generate these structures individually for all single mutants. And the second part of our goals to using, as the previous slide showed, electrostatic and shape descriptors from RBD structures correlated with experimental AC2 binding affinity, and these data used with protein-protein docking calculations. There are few to date, there are few the softwares which can use GPUs to run protein-protein docking calculations, and the protein structures are handled as rigid body. The one of the best of it, Class Pro 2, which is developed by a Hungarian researcher, Sándor Vajda, but he is in Boston University. And yes, our main goal is to try to develop machine learning based method that can produce deep water scanning experimental data in silico. So there should be no need to perform expensive molecular biology experiments, but everybody knows it's still a dream. And some words about the technical details. I mean, 15 minutes. We have the opportunity to use the Ampere 01 machine at Wigner Research Center for Physics. It has 256 CPUs, and it has 8 NVIDIA A100 GPU cards. And for AlphaFold database, it has a huge database, 2.4 terabyte. For the access time acceleration, we got a 5 terabyte solid state drive. So running time for one RBD model is about 50 to 20 minutes. So I can start temporary run per GPU card. So for a variant of RBD single mutant variant, we can finish it approximately a week. And thanks for my colleague and for the GPU team at Wigner. Have a good lunch.
For this nice lecture. We have a question from the Zoom. Ákos, did you compare AlphaFold generated structures with other methods, generating mutants with modular? Do you see what is the advantage of AlphaFold over conventional methods which are not so resource extensive? It's from Tamás Hegedűs.
Yes, thank you, Tamás. As I to thank it so to be honest, I didn't do any kind of detailed benchmark or comparison with other methods, but I know that, for example, the iTensor, the other competitor of this method, it's much slower than this AlphaFold, and the other reason is why we use this, the output, the quality of the output, because it has, I show that in this part, it has it produces very good quality models, so we don't need to for further structure refinement. Tamás, is it enough for you? Or okay, thank you.
Any other question? If it's not, thank you again for this
question.
I'm just wondering, how hard is it to actually create such, after you have the model, to actually create it in the laboratory? And is there like an ethicality concern over that type of thing?
Do you ask about the potential scanning? What? Please repeat your question.
If to actually manufacture these proteins, yeah, how difficult, and is it an ethicality issue?
So to tell honestly, I didn't try this, but it requires very state-of-the-art molecular biology laboratory and huge amount of money to buy the equipments and the enzymes, and it's all of them high quality and high-end techniques in molecular biology, and only the best can do this type of deep matter scanning experiments in the world. So it's expensive, and it requires hard teamwork and very skilled technicians and postdocs and researchers. So I won't be able to do this, to create a Nature paper or Cell paper, for example.
Your question? No. Thank
Okay,
you.
thanks again.
So, lunch until 2, right? Yes.
Igen.
Zsebembe tegyem, vagy? 1, 2, 3. Oh, 1, 2, 3, infinity. Okay.
So welcome everyone back on the afternoon session. Our first speaker is István Pap from the Wigner Research Center, and he will talk about simulating gold resonant nanoantennas for nanofusion. So go ahead.
Thank you. Hello, is it working? Like this? Oh, okay. Hello everyone and welcome. It's good to see everyone's faces again. I will talk about a project which has been recently started a year ago, which was already in the development before. In 2019, a group of people were already discussing this on a different conference. And by today, there are multiple people, even more people interested in the project. And we are thanking even for the Wigner GPU lab. This project aims for fusion, and you will understand it at the end why it is called nanofusion. So the thermonuclear fusion, we are aiming to achieve a clean energy, and we are trying to either maximize the confinement time or the pressure. So in order to achieve energy gain, in this particular case, we will focus on inertial confinement fusion. So we are trying to maximize compression. And here, there are multiple, in this section, there are multiple approaches. One is the direct drive, which actually focuses the laser beams onto the target, and an indirect drive, which focuses the laser onto an igniter, which also focuses which will be destroyed, and the destruction of that will then ignite the fusion pellet. So in the National Ignition Facility, they used in the older days a gold hologram, and they inserted the shell inside the hologram, and with 192 different laser angles, they destroyed the gold, producing X-rays, which then irradiated a shell called ablator, which then evaporated from the surface, compressing the target in the end. This indirect and also the direct drive has a drawback, namely the mechanical instabilities, like the Rayleigh-Taylor instability, which then in this case, most of the energy is lost because into the destruction of the pellet. In the last years, they actually managed to decrease these instabilities. They nearly reached the 1 Q limit, the dream limit. So from 1.6 megajoule kinetic energy, they reached 1.3, which was a great achievement.
but still the mechanical instabilities also will occur in the magnetically confined fusion chambers. This project combines two territories. One is from relativistic hydrodynamics theory, and the other one is from surface nanoplasmonic research, and we try to achieve a so-called time-like detonation, in which the phase points on the time-like surface are not casually connected. So basically, we try to achieve a full volume ignition. It is already done for example, in the direct drive also, when you shoot a target with laser, but unfortunately, this this section only extends up till 12% of the target. But if we manipulate the target's absorptivistic properties, then the nanoplasmonic research will come into the picture, which actually basically studies the small nanoscale antennas, gold nano antennas, also this experimental part of the project. There are people who can actually produce these targets, and our aim in this research lab is to prove the idea that changing these absorptivities, we can achieve at least 70 up to even at 73% simultaneous volume ignition. Our aim is to shoot with from a two-sided setup with a flat target in this phase from the two sides, and here you can see that our calculations prove that if we vary the absorptivity of the target, the energy can penetrate nearly to further than the middle, so nearly to the other side. I mean the theoretical part of the study, and for this and many fusion research particle in cell methods are used widely, and the main problems which can occur is that people never combined the nanoplasmonic part with the relativistic hydrodynamics part, and it is very hard to these small nanoparticles inside a particle in cell method. So the particle in cell methods generally look like finite difference time domain methods. So they update the fields at half times, then calculate the current deposition and update the fields to the full time steps. And generally, they solve the relativistic equation of motion under the Lorentz force. For example, we use this Bunemann current deposition, and the main other main attraction of this particle in cell method is that we don't use just point-like particles, because we couldn't use enough particles 10 to the 6 times 10 to the 23rd particles. So we need some trick, and that's why we use super particles that extend to outer cells. So the forces on the neighboring cell walls also act on the particles, but for in a lesser manner. So this is the simplest triangle shape, where you have 50% of the target in your main cell, and in the neighboring cells smaller part. And traditionally, people who study the surface Bosonic effects in theory, they also use finite difference time domain. However, the motion of electrons, for example, the collisions are indirectly taken into account in the dielectric constants. Thankfully, also there were people who actually understood the behavior of antennas. If we think about it, the antennas are smaller than the wavelength of the light, and they still can have a resonance, and this is an empirical formula in which we can determine the wavelength, the resonant length of an antenna which is in vacuum and resonates at 800 nanometers wavelength of light. The lambda, the resonant length of this nanorod, which is, for example, 25 nanometer in diameter, would be 100, half of this lambda effective, so 133 nanometers. And inside the peak simulation, with a very huge resolution, we usually do not calculate with this kind of resolution, but for presenting it, it looks like this. So here is the number density of charged particles inside these cells, which actually are the outer limits of the nanorods. And here in the simulation, we consider the charged particles gold ions, which had plus free charge, because we in this
in this approach only considered the conducting band electrons inside the nanorod, and we studied the lifetime of the nanorod, because lifetime meaning that the conducting electrons will leave the nanorod. So here you can see that they move up and down. So here the momentum distribution in the y direction. So in the oscillating direction of the laser light, and the electrons move up and down. And eventually, you will see at later times we have a smaller number of particles, and they also leave the simulation box. And here you will see the number density, so the number of the number density of electrons per cubic meter. So the black is the highest, so is the denser, and the yellow one is the lowest, but hopefully it's visible maybe here that electrons spill out of the nanorods, and they leave the nanorod, and eventually also the simulation box. Maybe here is a better one. So in different time steps, you see that the particles go outside. Some of them will return and some of them will leave. We used a flat light, and here we can see that when the nanorod's length is the resonant length, this lambda effective over 2, then we get a higher energy absorption, and the cross section up to 26 or 25 times bigger than the nanorod's size compared to the box size. Here we tested this also in finite different element methods, which are widely accepted in the literature, and you can observe that we have a similar behavior. However, it's very noticeable that in the finite element methods, the resonant with the resonant length nanorod will have a higher energy absorption at the end, which can also be explained that with the fact that in those simulations the nanorods will not get destroyed in the process. We also simulated in the UDMA. This is not a very satisfactory result, but I will show quantitatively is bad for my taste, but qualitatively. So here is a video from the older from the vacuum, from simulations with the inside the vacuum. The nanorod is inside the vacuum. The light comes from the left side to the right, and hopefully, yes, it works. Okay, I will slowly, yes. So
hopefully it is visible that in the vacuum, a lot of the electrons leave the nanorod, and it will shrink inside by the end of the simulation. And inside UDMA, in which we have the surrounding medium. Oops, sorry. Oops. To the end. Okay. Here you also see an oscillation. However, at the end, the nanorod will not shrink. And you can see also that after 100 femtoseconds, we will not have destroyed nanorod. And also interesting, yes. So here is the momentum distribution of the particles. So again, okay. Yes, so here you can see that the electrons go up and down. And in the end, so we jump to the end, we will not have completely destroyed the shape. And it will arrive to final in the middle. So, in conclusions, the vacuum model is in a good agreement both quantitatively and qualitatively with the widely accepted methods. However, the UDMA the model which contains the UDMA needs to be further upgraded also. Ionization must be included, and nuclear reactions and even the target compression will still be needed to be implemented in the end. So thank you for your attention.
Thank you very much. Just a very quick, very naive question. What do you think? When will you? When can you perform real field tests for, energy production? These results are very promising, I think.
Yeah, the first part of the experimental, the first experimental part of the big project will be probably when we reach to the level where it's designed to be able to put it in the Eli Szeged Eli laboratory. We are working on that, and we are hopefully in less than a year away from that.
That sounds very good. Great.
What's the main bottleneck computationally if you do these simulations? Is it time? Is it memory?
Time, actually time. Also, the memory part also depends on the resolution which we use. Here in this simulation, we used 5 nanometer resolution. 3 nanometer resolution, which is quite big if we consider that the diameter of the nanorod is only 25 nanometers. However, this can not even the COMSOL
uses a higher resolution because they also have this problem both the time and memory consuming.
So I had a question. I may have missed that jump in the talk. Initially, you mentioned that there was a larger gold nanorod and which was bombarded with lasers from the two ends, and that was used to
the larger one is
for pellet ablation.
So the larger one is the 133 nanometer one, which is in vacuum. But if we try to calculate, if you use a substance, which, for example, UDMA, which is a polymer used in dentistry, we actually test that. That's why I wanted to try to use the UDMA, because in the experiments we use UDMA to prove it in the experimental way. So in the Wigner lab in the institute, we shoot the UDMA targets, which are doped with these gold nano antennas. We shoot them with the laser. And we measure the crater sizes. And we already proved that the different increasing gold nanorod densities, you can achieve bigger crater sizes. And the only thing we still don't know yet is whether is it linear or not, because we don't have enough data about that. But so that is why I have two different nanoparticle sizes, because one is 133 because it's in vacuum, the first simulation, and the other one is the resonant wavelength inside the UDMA, which has a refraction index of 1.5 or so, 1.53. And in that case, the resonant length of this small nanorod, which resonates at the 800 nanometer wavelength, because we usually shoot it with this slide, is 85 nanometers. So this lambda effective is like 170 nanometers from this empirical study. That's why we use the two different size nanorods.
Okay. Further questions? If there is no question, then thank you, István, again. And our next speaker is Balázs Bámer, who is going to talk about numerical simulations of mirages above water bodies.
Can you hear me? Okay, thanks. Hi everyone, I'm Balázs Bámer from Wigner, and we together with Anna Horváth and Gergely Gábor Banatföldi made a small simulation of mirages over water bodies. Doesn't work. Does it work? Yes, okay. Short outline. First, I will speak of motivation, then the physics of the mirage and this phenomenon, then about the simulation, design and implementation, some words about the results and the possible future works. Mirage, or in Hungarian Délibab, is often seen in the nature as well as in urban environment. Effectively, it's always visible when the ambient air is cooler than the surface above its resides. And for mirage, we speak about inferior mirage, which means reflection is upside down below the real image. Sometimes in more complicated air circumstances, superior mirage can be also observed, but this is not the case. So this is how the mirage occurs. Here we have a larger object from the ground up to this point. This is the Earth's curvature. And in this case, we can see the whole object. So the Earth's curvature is not hiding any part of it. And we use a simple pinhole camera model here pinhole. And we can see that the upside down image is formed as usual in the pinhole camera from the whole object. But from its bottom part, also the mirrored object or mirrored image is formed above the normal one. This is the mirage. And here we can see the horizon or the ray coming from the horizon. And from literature, we had good measurement data from water temperatures above water bodies. This serves as our basis of our model. And we use a simple exponential thermal distribution above the surface. So this is surface level. And we can see that the exponential part is mainly in the bottom region visible or effective. Above it, the temperature is the temperature of the ambient air, and it can be constant. We use this formula for calculating index of reflection. We hold the pressure as constant, temperature varies as the height, with the height, and in fact, it also depends on the relative humidity of the air, but its effect is with the order of 2 magnitudes smaller than this part here, so we have neglected it. Okay, so this is the classic economic equation for ray tracing, which can give a general solution of tracing light rays or electromagnetic rays in inhomogeneous medium. This one, which can be derived, we have taken this from the literature into these two pieces of different equations. Here, this is the differential with respect of the location with respect to the path along the ray. And this is the differential of the slowness factor with respect to the wavelength. And the slowness factor is defined by this formula. And in this figure, we can see that if these are the equitemperature layers of the air, then light coming from this direction, this being the light wavefront, as in the original economic formula. It will propagate in two different paths, and in fact, we simulate or we solve these differential equations along each ray. This is our solution. This is a simple command line application with a standard C++17. It runs only on the CPU, but it utilizes all the cores available, of course. And we use eigen3 for vector algebra and GNU scientific library for solving the differential equations, and libpng for image input and output. GNU scientific library has this other solver, other I2 module, which we extended into a other solver GSL for a general purpose other solver for an arbitrary end condition. This was necessary because in our differential equations, the differential was this with respect to the ray length, but we need we need our solution at the intersection with some geometry. In our case, a billboard, because we are simulating a billboard scene from some camera. And to solve this, we use the adaptive Ungertutta-Fehlberg algorithm from the GSL, and as it can't handle but only the variable or the independent variable. We started from the beginning the integration, and it takes larger and larger steps. And one point is we passed our target. And this time we start the integration from the previous point, which is definitely not before the target. And we repeat the process again and again until we are in a predefined proximity of the target. And for this point, we say this is our solution. We have developed the general templated C++ solution for this problem, for solving this problem. And the computational cost is this, where x is the ray length until the target, and epsilon is the x is supposed to be larger than 1, and epsilon is the error we are taking the solution is supposed to be smaller than 1. That's why the minus here. This is an example run on the original RCA monoscope image. It was, I think, about 2 kilometers away from the camera, with air temperature 2 degrees centigrade and 13 degrees water. These lines will be important for the next slide. The green lines show the image limits when the ambient temperature is equal to the water temperature. Red line is the horizon. You can see the red line passes where the normal and the mirrored image touches each other. And we can also see the bottom part of the object is invisible. That's because we use the curved Earth model. And here is a real-life simulation. This was the original photo of the Balaton, photo taken from Keszthely in direction to Balatonfenyves. These are the trees on the radial line. And we can see the bottom of the image is missing. It's around 60.8 kilometers wide from Keszthely. And I was lucky enough to take a photo from 50 meters elevation from above so that the Earth curvature does not disturb the image used, that original image for the simulation. And here are the different cases for simulation with ambient temperature equal to the water temperature and with the similar conditions as in the real case. The water is just copied there, so that this is artificial copied here. Our goal was to build a simple temperature model for maze simulation. This was an exponential model, and develop a general C++ library to solve the this differential exponential problem, and also develop the simple data swap running primarily under Linux to simulate the mirages, and the code is available at a GitHub repo and is mainly for educational purposes. And possible future work can be image processing of simulated images and also real-life images to make an AI capable of predicting the temperature difference between the ambient air and the water from the mirage visible on the image. Also simulated observed mirage over asphalt. Of course, it's not that complicated because we already have some asphalt models as well. Or implement the algorithm on the GPU. And perhaps the most interesting one, at least to me, would be use different wavelengths to simulate colorful images. And in this case, for example, the I think blue or red, I can't remember, but there was a real life photo in some article. So the different colors would behave differently, and for example, billboard half blue, half red would partially disappear because of the different reflection of the lights, the colors. And I can show you two animations if I can click it. These are the graphs of reflection index and temperature. And this is the other one, similar, but with the real life image. You can see the ambient temperature is increasing as within the previous example until there is no mirage at all. And he is on it to the GitLab repo. Thank you for your attention.
Thank you very much. Before turning to the audience to questions, have you considered the changes in the air quality in your codes? I mean, I guess that the refraction index can change significantly in a clean air compared to the smoggy air, for example.
No, that was not an aim of this simulation. But thanks for the idea.
Maybe a remark to this, that we checked the literature, and the most thing which will affect on this is the humidity, which is basically very high in the close to the surface of the water. So what you said is, would we have to take this into account if we will do other simulations with concrete or solid surfaces, like in an urban environment? Yeah.
Thank you. Any more questions? If there are no more questions, then thank you again.
Thank you.
So let's move on. Our next speaker is Tamás Haba, who is going to talk about parallel computing for determining stable parameter domain in mechanical applications.
Okay. So, welcome everybody. Good afternoon. My name is Tamás Haba. I'm from Budapest University of Technology and Economics. And the title of my presentation is Parallel Computing for Determining Stable Parameter Domain in Mechatronic Applications. So, the field of mechatronic engineering integrates mechanical systems and digital control. And one of the most common tasks in mechatronics is position control. In position control tasks, the main design criteria are speed, accuracy, and most importantly, stability. Stability in a mechanical system means that the payload must converge to its final position and no unbounded vibrations should occur. And in design and stability analysis, we have considered the mechanical structures, friction effects, and the sampling effects of the digital control. So take a look at this simple 1 degree of freedom model with a mass and the Coulomb friction, which is positioned by a control force. Here's the equation of motion. As you can see, because of the discontinuous characteristics of the Coulomb friction model, the right-hand side of this differential equation is discontinuous. So this introduces a switched dynamical behavior in this system, but this isn't the only switched dynamic effect here, because if we implement position control by sample data full state feedback, then at every sampling instant, the control force gets updated. So that's another discontinuity, another switched dynamical effect in this system, which makes stability analysis really difficult. So the main question of this topic is how to determine the control parameters to ensure stability. So for example, if we choose some control gains and initial conditions, this can result in stable vibrations, like in this case marked with A. But some other parameter combinations with other initial conditions result in unbounded vibrations which are unstable. The main task here is to determine the whole set of parameters, which includes only stable dynamical behavior. So how can we do the stability analysis? There are basically two main methods. The first method is the analytic approach. So analytic methods determine the stability condition as a mathematical formula, but this mainly works in bad behaved situations, for example, in linear systems. But in our case, this system is nonlinear because of the Coulomb friction model, and we don't want to neglect the friction effects here. So we have to stick to another method, which is doing stability analysis by simulations. We can easily simulate nonlinear systems, but one simulation only gives us information about one parameter combination and one initial condition. So in order to determine the parameter set or stability region, we have to do a whole bunch of simulations. And here comes parallelization in picture, because different simulations can be run on different threads. So we can parallelize the simulations here. Okay, but basically, how can we determine stability by running a simulation? We took inspirations from the Mandelbrot set, which contains complex numbers for which this sequence is convergent. Determining convergence of this sequence is basically doing stability analysis. And in the case of the Mandelbrot set, it's done by the so-called escape time algorithm. It says that you just start evaluating this sequence until you meet one of the two stop conditions. The first condition is when absolute value zk is greater than 2. In this case, it is proven that the sequence is divergent. The other stop condition is when you reach the maximum number of iterations. In this case, the sequence is considered convergent. So let's adopt this method to our case with the stability, with the position control. So you just start evaluating the system, start running the simulation, and the stop conditions are slightly different. The first case here, marked with A, is when the motion stops and the system reaches an equilibrium point. In this case, the vibration is stable. And the other stop condition is when you reach the time limit. In this case, we can consider the vibrations unstable, but it's not 100% sure, because it's still a little possibility that the system, that the vibrations are decaying very slowly. But choosing a high enough time limit gives us reasonably good and reasonably good results. So, like we did Mandelbrot set, one stop condition gives us an exact result for stability or convergent. The other one is just assuming that the sequence converges. So we don't have better solution for that. So we just stick with it. Okay, but there's another problem. The escape time algorithm is implemented with sequences, and our system is a mechanical system. It's in continuous time, so we have to discretize it. There are two methods for this. The obvious one is to discretize the time derivatives themselves, and this is the most common approach. For example, Euler methods or higher order ODE solvers like Runge-Kutta or another adaptive time steps methods use this approach. And this is the general approach to solve dynamical systems. But in our case, this can be problematic because, as I mentioned earlier, the right-hand side is discontinuous. So dealing with discontinuities is a big problem with ODE solvers, even with adaptive solvers. So try another method here. We did the piecewise analytic solution of this differential equation. In this case, we can derive the solution of this equation analytically and symbolically, and we can implement that in program and evaluate it very efficiently. So that the discretization is done, we can implement the escape time algorithm. let's talk about parallelization. The initial problem has an n-dimensional parameter space with initial conditions. And the first thing to do here is to divide this parameter space to a parameter grid. And then the next step is to flatten it. So every cell in this parameter grid corresponds to one element of this one-dimensional array of parameter combinations. And then we can run simulations on GPU, parallelized, and get back the results in a one-dimensional array. The last step is to map back the results to the original n-dimensional parameter space, and this way we can determine the stable parameter regions and make stability charts. We implemented this method in OpenCL, and the program consisted of two main parts. There's a host code. It is written in C, and it runs on the CPU. It does resource allocation, sets up the initial values, and then calls the GPU code. The GPU code, the kernel code, is written in OpenCL C language, and it implements the escape time algorithm. The key here is that every work item in a kernel code corresponds to one simulation, one parameter combination, and writes the results back to the result buffer, and then the host code reads back the results and further processes them. So as a result, we determined the stable parameter region for in this two-dimensional example, and this was done by 1000 by 1000 parameter grid. And as you can see, inside the stability region, if we pick some example simulation marked with B and D, you can see that the time functions of the position are stable, and the simulation outside the determined stability region are indeed unstable. So every simulation here at every parameter combination was done with 1000 iterations, and as you can see, it gave us very accurate results for stability. We compared this method with a CPU implementation, and it was 800 times faster approximately. So we are happy with these results. So just to summarize our work, the initial problem was the stability analysis of a sample data position control system. The first thing that we did was to discretize the problem, and then we implemented escape time algorithm and the stability analysis in OpenCL. We executed the simulations parallelized on GPU, and as a result, we get a very accurate stability chart for stability analysis. Okay, thank you for your attention, and if you have any questions, feel free to ask.
Thank you very much. Yeah.
So in contrast to Mandelbrot, you have a nice problem where a point's neighborhood is similar results, and you're using that, but that's fine. That's just a comment. But the question is, so you are running basically the stopping. There are two conditions, am I right? You either stop or you wait some time. And these, of course, take different time to evaluate. Sometimes you stop early. You don't have to wait at the full calculation. But on the GPU, your time is controlled by the longest task, am I right?
Yes.
So did you try to study how much time you potentially might save if the short tasks could be sort of finished earlier and the same unit could be used for other tasks?
Yeah, thank you for your question. I think it's still room for improvements, but the execution, the parallel execution in this case. So yeah, this chart is very smooth. So scheduling this problem usually works by simulating parameter combinations that are
neighbors. So there are still simulations that are finishing earlier, and the kernel executions that are just wasting time. But in GPU, there's still this implementation. We haven't figured this optimization out yet. So I think there's still room for improvements.
I have two questions. First, do you have a comparison of the, or do you have a CPU-only version?
Yes, we did a CPU implementation.
And do you have a comparison, the CPU-only versus GPU implementation in speed?
The GPU implementation was approximately 800 times faster.
And another question, you mentioned this 1000 by 1000 grid. And do you run the algorithm, the escape algorithm for every parameter pair?
Yes, so every parameter combination ran for 1000 iterations.
So you run a million parameter combinations 1000 times.
Yes, exactly.
And have you considered implementing some sort of search algorithm to avoid at least part of the 1000 by 1000 runs?
There are implementations, CPU implementations that just work like dividing the search region, and it's like interval halving, but in higher dimensions. But in our future plans, we want to implement this method on GPU as well.
Okay, thank you.
Okay. So the 800 times speed up looks a bit fishy. So it's a nice and big number, but it's really hard to realize that kind of speed up. So for the pure CPU implementation, it is very easy to. I assume that was a serial CPU implementation.
Yes.
Like it's if one checks to parallelize that on a CPU, which is fairly simple, given I don't know, like parallel STL, it's like one line of function, and it takes care of with yes, if the application is organized well enough, then it comes at the cost of one line. But then one can do like a socket per socket or a performance per watt comparison for the two.
The CPU realization was a naive implementation, so it was just single-threaded, and we did not utilize vector registers or similar things. So it's just a basic benchmark. So
one fairly decent comparison is to run it through a OpenCL CPU runtime like Intel's, which automatically takes care of vectorizing the code. Like it runs one work item down one AVX lane, and that way, if there isn't many thread divergence, then it comes as close as a fully vectorized code as one could reasonably get.
Okay, in the future, maybe we'll try that in comparison. Okay, thank you.
Okay, so let's move on. Thank you again. The last speaker of this session will be Grady, who is going to talk about full 14 level simulations of rod drop experiment. You will read that.
Am I being heard? Excellent. I'm not used to talking in the microphone. Usually I'm teaching a class without a microphone. So I'm trying to get my voice level right. I'll read your faces, whether it's too loud or too soft. And he will regulate me. So it will have absolutely no consistent effect. Very good. Okay, so I'm going to talk about simulations we did on nuclear reactors using GPUs. It's a Monte Carlo code we wrote. And I'll try to explain some basics about how that could be done. Last time at the GPU day, I gave the exact same presentation regarding the first couple of like 10 slides, but I'm trying to highlight the differences. And at the end of that presentation, we reached a wish. We wanted to simulate a full reactor, like what we have operating in the PUCS nuclear power plant site, with full realistic details and everything. But we knew that we don't have the computing power. But that was just after Christmas. Usually I never pick up my phone during holidays, but Gergő called me and by accident I picked up. And he told me, okay, computers are there. Yeah, that was very weird. So I picked up the phone and he said, okay, there is the computer. If you want to be the early bird trying it, you can. There is someone else, also a candidate. Do you want? Said, yes, 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 yes. So we immediately submitted our calculations and we just continued the very same work. So what will change in my presentation is basically the results, and I omitted some part of it. So, okay, there is a group. Now the group is bigger than last time. It's inversely proportional with the funding we receive. Now the funding went down to almost zero, so maybe that is the peak number of group members. Loads of students mostly, and some senior members. We are from the Budapest University of Technology. We have a reactor. Whoever wants to come and visit, it's free to visit, just you have to check in. So what about this code? We wrote this code called Guardian. It stands for GPU Assisted Reactor Dynamic Analysis. When I was looking for a better acronym, it only gave me one acronym that was really nice. It was Meltdown. Now it is a code for reactor safety. So that was not a nice acronym, so we went for Guardian. Other people has written Monte Carlo codes since the beginning of developing nuclear bombs, basically. What is new is that we have a dynamic Monte Carlo code, so it's time dependent, and it will receive thermohydraulic feedback as well. So neutronics produces heat, boils water, that will change neutronic parameters, that will give a feedback. So that is the idea. So if you have an accident scenario, it's very hard to calculate because you have two very difficult systems coupled non-linearly. What will come out? Is it still safe or not? So that's the basic aim. Other people have started doing this dynamic Monte Carlo. Like 10 years back, I started it with my former PhD supervisor. Can we do it directly? Everyone does it not by Monte Carlo, I will tell you about it. But whoever does it with Monte Carlo does it in a quasi-static way. So you have time steps and static calculations, one after the other. What we tried, let's do it dynamically. So neutrons go as in nature. And the only question, okay, we were sure it cannot be done. But the question was, can we estimate how much computing power can you will need for it? And at that time, it was like that. Then they put it in an already existing Monte Carlo code developed in France, that's Tripoli. They also put it in a Finnish code in Serpent. And they could calculate with huge clusters of CPUs. And then we tried it on GPU. And immediately we reached the stage, and it was just a couple of months back, when we could take a full nuclear reactor core, very realistic, and it did run. It needed the Wigner cluster, the new GPUs, the A100s, 8 of them, but it ran. And that was first that we could do a full simulation like that. So we used to run on old GPUs because the university procurement laws did not allow us buying new ones. Now we have a fairly new but not high-end cards, and we use the Wigner cluster. We are also waiting for the Commander cluster for more GPUs. Okay, so why can you do neutronics calculation on a GPU? Because you have similar physics, and that similar physics, I mean, to graphical applications. So when you look at visible light, they
transport in along a line, and they have interaction at surfaces, and then they change direction, maybe color as well, and they go in a different direction. So with ray tracing, you go around. Neutrons do the same, but instead of having interactions at surfaces, you have interactions inside a material. What could be difference is that for neutrons, the interaction physics changes very much with energy. And if you look at a neutron, you start with a high energy neutron. It has to slow down before it induces fission. And in the course of this couple of orders of magnitude energy difference, you will have a couple of order of magnitude change in reaction cross sections as well as the reaction interaction probabilities. Also, neutrons need more parameters, and also computer graphics needs approximate solutions. If it looks nice, it's okay. Neutronics, I just gave an example last time, it was the same, that if you have a 15 micron difference in material, if you put a very thin foil of cadmium in your reactor, it will immediately stop your reactor. Abruptly, you will lose 20% of the power and it starts decreasing. So you have to be very accurate. And I will also show that with very small changes, you can lose the criticality state of your reactor. So if you just do very simple math, you have neutron starting, you have a fission produces 2.5 neutrons. I tried to put a half neutron over there. And then some of them will escape, some of them will get absorbed, and some will induce new fission. From 1 neutron, on average, you want to get 1 neutron back. Even if you make 0.1% error in this criticality, in 1,000 generations, that will take approximately 1 second, you will get a 2.7 times power increase. So even if you make a very small mistake in your calculations, your power output will be very, very different. So you need very high accuracy. In real life, you would not be able to control a reactor with these settings, but you have so-called delayed neutrons, some neutrons that emerge a second after the fission event. And that will be 700 PCM of the population. 1 PCM is 1,000th of a percent. So that comes later free. That means you have time to control your reactor. If you do the simulation, that gives us some problems because the time scales are different. You have the prompt neutrons emerging immediately and some neutrons coming free a second later. Neutron interactions are very fast. From one fission to other fission, you will get 1 millisecond on average of time elapse, and then some neutrons jump time 1 second later. You have to get that balance right. So you have this time-dependent system, and you want to solve this equation. I just put it on because everyone puts on equations. In this section, everyone was showing videos. I will also show some videos. So it's an integral differential equation. How would you solve it if not by Monte Carlo? You can use finite differences, finite elements. So in the right-hand side of this presentation, you see our training reactor model with finite differences. So you see the geometry is like, well, just blocks. And that is some state-of-the-art simulation. You look at the left-hand side, that's the Monte Carlo model. You can take into account all the details. What is the price that you pay, running time. What is even more, I will skip this one, interesting, but I will skip. What is more interesting is the interaction probabilities. So you see a logarithmic scale. That is the energy. Fission neutrons are born here. And for a new fission neutron to be produced, that happens somewhere here. So you have to slow down the neutrons. On average, about 30 interaction has to take place before you get from high energy to low energy. And if you look at the interaction cross sections, they change a couple of order of magnitudes. This part is very interesting. It's called the resonance region. So even if you make a small step in energy, a couple of orders of magnitudes, interaction probability changes occur. So how to simulate it? You have to simulate it very accurately. Or if you use finite differences, you just divide this into 2 groups. 2. And say, okay, let's have an average cross section here, an average over there. And that's how you do nowadays time-dependent safety calculations for reactors. The fun part is that it's accurate. So we don't have accidents. Of course, they always have to estimate how to stay on the conservative side of all the safety estimations. And that's very, very hard. That is the art part of these simulations. If you have to condense all this information into two constants, you have to do it very artfully, and they do it. And the generations of old reactor physicists do that. Maybe they have to be replaced because you have not many young scientists coming, so maybe you have to replace them with artificial intelligence. But that is the common practice now, and we want to replace that with our Monte Carlo calculation that needs no intelligence. Okay, I'll skip that one. There are very nice tricks that we have to apply to keep this calculation stable. And we do that. If you try to just simulate it like it happens in nature, you should get the red curve. What you get in reality is the blue curve, because statistically it collapses. We have 4 or 5 orders of magnitude less number of samples than neutrons in a real-life reactor. So just an analog mimicking nature way, you can't do the simulations. You have to have smart tricks. That's called variance reduction. That is my field. And I also thought that we have this timescale problem we have to bridge. But now what I want to talk about more in detail is the simulation we started. So it's the POX nuclear power plant site. We have 4 units over there. That is unit 4. And a couple of years back, there was this startup experiment at the beginning of each campaign. So new fuel loading. You have to perform loads of safety experiments. And one of them is that you drop all the control rods to stop the reactor. But let us assume that a single one, the most important one, will get stuck. Will your reactor shut down in time or not? That's the question. They routinely perform this experiment, and we wanted to mimic this. All the other competitors, they could do the simulations for full reactors, but not realistically reactors. So that meant the isotope concentration was not realistic. Or they could do realistic isotope concentrations, but for small reactors. We managed to do both in the same time. So we have this VVR reactor, that is the Vodovodanoi Energetický reactor, or water-cooled, water-moderated reactor. The type number is 440. That means 440 megawatts electric power is generated. Now, it has been operated a couple of years back, initiated by the reactor physicists at the nuclear power plant site, that they could make some better loading, and they could raise the power of POX to 500 megawatt electrics for each unit. And for that, you needed more realistic reactor safety calculations. And for that, that is the practical relevance of the simulations that we did. So we aimed at this one, and we had a single card that was not that bad. And before we got this offer to run on the Wigner cluster, it would take for us 4 weeks to simulate 4 seconds of this experiment. And this experiment lasted 12 seconds. But we still felt we are the first, so we have to publish it somehow. But then I got the phone call, and what we could do, it would take just 2 weeks. We could simulate the full 12 seconds, and we could do 8 independent simulations to estimate the error in the calculation. And that last part was the most important for us, because I think that is science. If you can simulate something that looks like reality, well, yeah. But if you can tell how accurate you are, I think that's something. So it is very easy to get that published. Okay, so how does that this model looks like? So this is the power plant at POX, top view and the side view. All in all, you have these very small dots. Every single one is a fuel pin, 2 meters high and less than a centimeter wide. This is the side view. In total, 44,000 pins are inside. You have to model them and know the water around and the cladding of each pins and so on and so on. So altogether, that is the impressive number of surfaces, cells, lattices, universes, and materials we had to use to build a model. Okay, the truth is that we got the model from someone else. We have to just adopt to our code, but well, it's still a lot. If you take a look at one of these hexagonal assemblies, you will get 170 something pins inside. That's here. And at the power operating, they changed some of these assemblies to include gadolinium. That's a so-called burnable poison. So neutrons will burn it out, and then you can keep them longer inside the reactor. So you had to model them separately. That was still, I'm not saying a piece of cake, but it was doable. What was hard that we had to also model this, that at each fuel loading, they will not replace every single fuel assembly in the reactor. They only replace part of that. And some of them, that the less burnout parts, go to the inside, and the burnt out ones are taken out, and new ones are introduced in the sides. So you also have to calculate the previous years, what part of the fuel has been burnt out and what new isotopes were created. That's a tedious calculation. We did that. It's not true. We got it, these results, but it was still very hard to take them into account. Hundreds and hundreds of isotopes with different constituents in every single fuel cell. Now the colors indicate the different material types due to burn-up, and that is the same 2 pins. So okay, so we have all the details. We started simulating the measurement. This is again the reactor core. Here the red one is the control assembly that gets stuck. You have detectors here and there and there, and that again a step that the other competitors couldn't do. That we not only simulated the power of the reactor time dependently, but the detector readings outside the reactor. And that's very hard because neutrons inside the reactors run around, but you have to transport them out to the detectors to get the readings. So you have to get, and that we have to do it very accurately. How was it? It was done realistically. It was a sensitivity factor pre-calculated. So, for example, for detector 14, we calculated one fission on average will cause how much of these detector readings. If you look at the numbers, it means that 1 out of 10,000 particles, even at the closest pins, will give you a reading and the detectors. So if you want to get sensible relative variances for your results, you have to calculate actually the neutron population also at the edges of the reactor. Again, something that is not very easy. So it's just a magnification. So you see that even the highest one decreases so fast, a couple of orders of magnitudes in sensitivity. Okay, so now the videos I promised. So. Okay, so this is the geometry. You have the core, you have all the control rods dropping in the reactor core. These control rods are made of neutron absorbing material. And somehow you can repeat it. Well, maybe I will. I'll show this one repeats it, right? Okay, so now what happens is not only absorbing materials getting inside the reactor, but also fuel rods are pushed out of the reactor. So you remove some fuel and then introduce some absorbers. And you see now these absorbers going in, the fuel rods going out. These are just the guiding tubes, and one of them gets stuck. So that is the process that we wanted to simulate. It's 12 seconds. Well, this takes only a second or two when all the rods drop, but then the neutron population is still active, and then you want to wait until they die out. So dropping of the rods takes 1.5 seconds, I think. Okay, so that is the geometry. And now this is one static simulation. With color codes, you see the power distribution. In the inside of the core, you get more power, but you have some rods that are absorbing, so you don't have so much power over there. We cut it just for visuality, and you can look inside. You have all the 44,000 pins separately, so you can look inside of them, and there is air inside. So that is the detail of the simulation. Now, this is half of the core. these blue pins are the gadolinium pins, and now you have all the rods falling in. At the beginning, you have the control rods that maintain the stable power, so they are already introduced somewhat, and then the safety rods come later, except for one that's over there, where the power is maintained because you don't have the control rod. Perhaps another one. This is a side view, all the rods falling and then the power decreasing fast. When you compare the result, looking for one this one. So if you look at the detector reading data, you will have with blue the measurement, how it evolves in during these 12 seconds, how Guardian calculates it, and we asked the Functional nuclear power plant people to give us their in-house code that they use for safety analysis, and they had different settings with the red and the yellow curves. And they are very good approximations. So we are not trying to say, okay, you calculated wrong, we calculated right, but more like we have a different method of calculating and we can verify your results with all your approximations of only two groups of cross sections, two energy data, and so on and so on. So that is more the idea. And the simulations went excellently. Okay, so those were the videos. So last year, I showed this graph. We could get to this point 3 seconds without the Wigner cluster, and now we could get to the actually 20 seconds, almost 12 seconds for Guardian, and we could repeat the simulations 8 times. And as I told, that was the important feat, that we could check the relative variance, because we want to couple this calculation to thermohydraulics. And if you have high statistical variance coming from the Monte Carlo method, and then that changes the temperature like 10% up and down, how stable thermohydraulic calculation would you get in 3D? Well, not well. So we had to check how well can we calculate. And it turned out that for the relative variances of the detector readings, we stayed at a couple of percent. But we could also check in space how our relative variances go. So that was the first picture we got. The blue is excellent. It's below a couple of percent. It's very good. But what these red dots looks like some disease. And indeed, that was a disease, a sampling disease of the delayed neutrons, the neutrons that come free with a bit of time delay. It was not easy to sample them in an adequate way. So we had to improve the techniques to come up with this figure afterwards, that only at the very edges of the reactor you get high variances. It's percents, 20%. But if you look at the blue, it's about a couple of percent error that you get in 1/60th of a fuel pin. That level of accuracy was really not expected. So that means that we can really couple this with thermohydraulic calculations. So the ongoing research is now targeting that. We have now thermohydraulic simulations going, and we are trying to feed it with data with statistical variance. And we are trying to check how well does it converge. And again, there we got more like a positive surprise than a negative, that with this low level of error, this convergence is not affected. So with this innovation, we went for an innovation prize targeting the safety of nuclear reactors, and we got some prize for it. And one funny aspect was that I got this glass thingy with engraving of the prize, and we got it for the safety of reactors, but there was a typo. So it now reads safety or reactors. But we got a prize for it, and I think that's interesting. But for this GPU part, that is going to be the last slide. How long does it take to run the calculations? With the 5-year-old cards, it take for 1 second of real reactor time with the full burn up. So the full isotope detailed simulation, 820 hours, not really doable, even if you have 4 cards. We have the 3090, it would take 48 hours per second, tolerable. With an A100, it would take 22 hours. If you would not take into account the burn up, so just a fresh fuel calculation, it would go down to 5 hours. So if you just do simulations, well, would this reactor concept be good and safe? You would do it very fast. 5 hours is nothing. These transients are very fast, only a couple of seconds, or maybe 10 hours on the 3090. But those 800 results are disappointing. First of all, we got only 50% of the thread use. The reason is that we eat up the registers because of the many neutron particle parameters. So 50% of the threads are stalled. But another more alarming problem is that we expected, because of the double precision performance difference, a factor 20 speed up. And we only saw maybe a factor 2. So we have to work now on our algorithm to be able to use high-end cards, because it just doesn't run fast enough. On the other hand, we need a huge memory capacity. So below 24 gigabytes, we cannot do full reactor simulations. So what is ahead of us is still a lot. But what we could achieve was also recognized by the international nuclear community. So that is the end of my talk. Thank you for listening. And if you may have questions, I'll try to answer.
Thank you very much for this very interesting talk. Questions?
The question is, why should I call you next Christmas? So what is what is the next step in this?
Well, we are heading towards coupling with thermohydraulics, and the thermohydraulic part is not on GPU. So we have to work on that. But we also have other ideas. Our group is also researching other GPU extensive tasks, that is more in medical imaging. So we have wrote Monte Carlo codes for medical imaging, CTs, isotope diagnostics, or recently proton therapy, proton imaging. We are also is very interested in artificial intelligence aided medical image processing and medical image reconstruction. So how to build from MRI measured data the image what the doctor sees. And for that, we need high GPU computing power. And we also have tentative ideas of doing hydrodynamics with particles like neutrons, like particles. It's called smooth particle hydrodynamics, and we are very intrigued by that to go for that. So we do. At the end, we would have a full Monte Carlo code for reactors, Monte Carlo neutronics, and Monte Carlo hydrodynamics. But who knows? Just call me. The important part is call me.
I find it very interesting, the difference between the A100 and the RTX 3090 performance. So you mentioned that it is a register use that you suspect as a problem on the A100. But can you maybe go into a bit more detail with regard to that? Because I'm not 100%, I don't have the specification in my head currently, but the SMs on the RTX 3090 and the A100s are very similar, right? So they have roughly the same size of register file available.
We could, on the A100, we could have we could make a very clever buffering using the L2 cache. And that's how we got the performance. So we had to do an extra trick. What we suspect that our algorithm is bad. We are tracking parallelly some 1 million particles. And if one particle has many, many interactions, it will stop all the others. So we believe that is the main problem. And it's an additional problem that we run out of registers. So we do hope that with a different algorithm structure, we can get a factor 4 or 5 speed up. And that is the main suspect. Because we use many double precision arithmetics, and we were expecting the A100 to deliver a lot better performance. It did not. So it must be the reason that we do a bad parallel workload balancing. of course, we knew that it was not excellent, but we didn't know it was so bad. And it was very hard to rectify. So we have all the ideas to try, but we haven't started yet.
Any further questions? If there is not, then let's thank David again.
Okay, thank you.
And thanks for all of the speakers of this session. And now enjoy your coffee break.
Is it okay?
So, good afternoon, everyone. Let's start our last session. Our first speaker is Emese Kővári, and she will talk about the resonance structure of the trans-Neptunian space. So, go ahead.
So maybe this way, does it work already? Or, okay. Sorry. Okay. All right, so do you hear me? Great. So yes, I will present you our recent results on the resonance structure of the trans-Neptunian space. And the co-workers of the collaboration are Emese Forgács-Dajka, Tamás Kovács, and Zsolt Sándor, my supervisor. Anyway, I am a PhD student at the Department of Astronomy at ELTE. And maybe a preliminary thought before I start that in our case, the computations were merely as a tool to receive quickly the results, but we put the emphasis elsewhere, namely on the results and their interpretation. So let's start by defining the trans-Neptunian space, first of all. We call the populations of icy, rocky planets that reside beyond the orbit of Neptune trans-Neptunian objects, or TNOs for short. So that is, they reside between 30 and about 2000 astronomical units. But since this trans-Neptunian space is not a homogeneous one dynamically, it's worth making some further distinctions between its parts. The innermost part is called the Kuiper belt, hosting asteroids similar to that of the inner asteroid belt to be found in between the orbits of Mars and Jupiter. However, this outer asteroid belt is far larger than the inner one, more densely populated, and the average object size is also bigger in this case. After the Kuiper belt, which extends about until 50 astronomical units, we find the so-called scattered disk objects, which are characterized by quite extreme orbits in terms of orbital eccentricities and inclinations. And this region ends at about 2000 astronomical units. This is the inner boundary of the so-called Oort cloud. Actually, the inner part of this cloud is disk-like. However, the outer part is already has a spherical structure. So in our research, we considered altogether almost 4,200 trans-Neptunian objects, or TNOs, between 30 and 2000 astronomical units. And you see the distribution of these objects, I mean the eccentricity and the inclination distribution of these objects. And what's important to note here is that eccentricity is as high as 0.4 and inclinations as high as 20 or 30 degrees are not rare either, suggesting that this region is dynamically quite active. And this already brings us to the importance of this domain, because we can say that it serves as a reservoir of dynamically unstable bodies, which, after being rejected from this region, can migrate inwards in the vicinity of terrestrial planets and then become either near-Earth asteroids or even potentially hazardous asteroids. So that's fundamental to understand the underlying dynamics of these faraway domains. All right, and as for the dynamics, it's shaped to a large extent by the different kinds of celestial mechanical resonances, primarily by mean motion resonances. to understand the concept of mean motion resonances, one has to start by defining defining the mean motion commensurabilities, when the ratio of the mean motions of two bodies, the mean motion is actually the average angular velocity of a body. So these mean motions labeled here by n and n prime can be approximated by the ratio of small integers. So according to this formula here, n over n prime will be approximated as p plus q over p. Later, the q will be called as the order of the resonance, but so far it's not a resonance, only a commensurability. So this formula suggests that if this is fulfilled, then there will be a periodic repeat of particular orbital configuration when the two objects being in a mean motion commensurability are in conjunction. So this property is illustrated in this figure here, showing an example of a 2-to-1 commensurability. That is, the inner body, which is an asteroid A, will complete exactly 2 revolutions around the Sun during one Jupiter orbit, because the outer body in this example is the Jupiter. So this is the initial configuration with the conjunction of the two bodies, and after 1/4 of the Jupiter orbit, the arrangement will be such. After 2 quarters, you see this configuration, 3 quarters, and after one entire Jupiter orbit, we receive again the initial configuration, which is the conjunction. So basically, this is the mean motion commensurability. However, it's important to note that in reality, the conjunctions are not as precise as indicated by this illustration here. However, they take place rather inside some conjunctional islands along the orbits. So, for example, in the case of a third order commensurability or later resonance, there will be 3 such islands situated along the orbit. And a sufficient condition for a mean motion resonance will be that these islands are separated. And to formulate this property, it suffices to introduce the so-called critical argument labeled here by theta, and the definition of it will be like this. To say that the islands remain separated, it's enough that this critical argument vibrates or oscillates around the mean value with a vibrational amplitude less than 180 degrees. So in this pair of figures, you see that if the vibrational amplitude of this critical argument is low, then the islands will be well confined. However, when there is an increment in the amplitude, then the islands will be more elongated. So if this vibrational condition is fulfilled, then we can call the commensurability a mean motion resonance, abbreviated as MMR. All right, but the question is how to rapidly identify these mean motion resonances. For this purpose, MSF, Forgács-Dajka, and her co-workers elaborated a method that enables the fast and quasi-automatic identification of mean motion resonances. It suffices to plot the mean anomaly of one of the objects involved in the mean motion resonance versus the mean longitude, the difference of the mean longitudes of the two bodies. And whenever stripes appear on these plots, we can say that it's a mean motion resonance. And by counting the intersections of these stripes with the horizontal as well as with the vertical axis, we can deduce those small integers that were seen in the previous slide, so P and Q. We applied this method in the case of the 4,000 TNOs considered in our sample. And and came to the conclusion that among the resonant TNOs, there are two groups that's worth making some distinctions between, because in the first group, we classified those TNOs that exhibited resonant variable or resonant angle that liberated throughout the whole integration time span. A nice example for this is actually Pluto engaged in a 3-to-2 mean motion resonance. However, we found several TNOs that were characterized by a critical angle that did not liberate throughout the whole time span, but these objects were only captured in resonances temporarily. An example is given here, which is not only rejected from the resonance, but then altogether from the system after some time. All right, and now let's see how mean motion resonances are related to the chaotic behaviors, or how can they stabilize or destabilize the system. So chaotic diffusion in celestial mechanics is the drift of a phase point in the phase space, which process can lead to orbital instabilities, but not necessarily. Yes. And it's worth distinguishing between the slow or Arnold diffusion and the fast diffusion. In the case of the former one, the perturbations remain small, and the chaos is confined to thin layers around single resonances. So, for example, in this enclosed figure, you see several mean motion resonances, and at the boundaries of them, we find such slow diffusional processes. So these regions are characterized by a slow rate of diffusion. However, in the case of fast diffusion, which can be found, for example, at resonance overlaps in the upper right corner of this figure, when several mean motion resonances overlap one another. In this case, the perturbations grow very large, and the chaotic domain is well extended. Yes, and now it's important to mention that an efficient but very simple chaos indicator can be defined through calculating the difference between the maximal value of the eccentricities and the minimal value of it by achieving the maximal variation in the orbital eccentricity. This is indeed efficient chaos indicator, also used in this figure, and we too use this in our research, among others. But this chaos indicator does not enable to quantify chaotic diffusion. For this purpose, we had to introduce probabilistic chaos indicators, as for example the more classical one, which is based on calculating the time evolution of the variance of some phase space variable x, labeled here by x, and by definition, it equals 2 times the chaotic diffusion coefficient, labeled here by d, times the time. And thus, by taking the time derivative of the variance of the variable x, one achieves the diffusion coefficient. A similar but only recently applied method, at least in celestial mechanics, is the usage of the Shannon entropy. Yes, so this concept was introduced in information theory. However, in about a few years from now, astronomers also started to use it to quantify the diffusion coefficient. So we need a trajectory, and to follow the time evolution of the trajectory, or at least the time evolution of the trajectory as projected onto some plane. So we can also denote this trajectory by x here. And in order to follow its time evolution, one needs to construct some partition of the phase space, or some section of the phase space. So, for example, in this simple example, you see a two-dimensional section of the whole phase space and a partition containing altogether 9 cells. And at discrete time intervals, the trajectory will fall into some cells of this partition. And by counting those points that fell into certain cells of the partition, we can use this formula here, where nk denotes the number of trajectory points that fell in the key cell of the partition, and so on. Uppercase n denotes the total number of the trajectory points. So actually, these expressions here give us some probabilities. All right, so according to this formula, one can calculate the time evolution of the Shannon entropy of some trajectory. And similarly to the case of the variance, one can deduce the coefficient for the chaotic diffusion by calculating the time derivative of the Shannon entropy. And by taking the inverse of these two types of chaotic diffusional coefficients, one receives the characteristic times of stability. All right, and after that, some words about the computations. We carried out direct long-term integrations where we use the barycentric coordinate system, including the Sun, the 4 giant planets, and a massless particle that was, well, not massless, only massless in the case of test particles. However, this small body could also be a TNO among the 4,000 TNOs altogether. So a barycentric coordinate system means that the center of mass was the origin of the coordinate system. We used a embedded Runge-Kutta-Nystrom integrator with a tolerance 10 to the minus 14th. And the total integration time span was as long as 100 million years in the case of the individual TNOs, and 200,000 years in the case of test particles, which we used to create dynamical maps. And you see also some details in connection with the calculation of the Shannon entropy. But maybe, I don't know how much time is left, but let's move to the results. So first of all, I show you a figure presenting the distribution of the 4,000 TNOs in the semi-major axis and eccentricity plane. What is remarkable that there are, well, actually, first of all, you perceive that there are 3 colors used in this figure. Those TNOs that are colored by color gray are non-resonant TNOs. However, all the colored ones, so either colored by blue or pink, are found to be engaged in mean motion resonances. This is quite a remarkable number of the whole population. And the difference between the colors is that those that are depicted by color pink are only short-term mean motion resonances, whereas those that are displayed by color blue are long-termly resonant TNOs. And then we highlighted the most those mean motion resonances that hosted more than 10 TNOs as their members. Maybe the most accentuated such mean motion resonance is the 3-to-2 mean motion resonance hosting the Pluto itself, and after this we call these resonant objects Plutinos. And then maybe another remarkable one is the 2-to-1 mean motion resonance. This population is called the Plutinos. So it was interesting to see the difference between those TNOs that exhibit short-term and those that exhibit long-term mean motion resonances. For this aim, I show you two examples of the long-term evolutions of the TNOs. So in this first set of figures, you see the time evolution of the integrations in the case of Pluto. In the upper figure, that's the time evolution of the semi-major axis, and then you see the eccentricity, inclination, and the libration of the resonant angle or critical argument. That's the figure used to identify the mean motion resonance. In this lower bottom, in this bottom figure or panel, you see that region that was visited throughout the 100 million years of integration in the semi-major axis and eccentricity plane. And I would like to emphasize here that you see on the right two figures showing the evolution of the Shannon entropy and that of its derivative, its time derivative. What characterizes the high stability or highly stable nature of Pluto is that it's the time evolution of the Shannon entropy reaches more or less constant value after quite a short period of time, and then it remains more or less constant, and the derivative decreases very rapidly to zero, and accordingly you see the reduced characteristic times of stability being very high. However, in the case of a short-term mean motion resonance, you see that after being captured into the mean motion resonance, the time evolution of the Shannon entropy is such that it decreases, so showing the capture. But after being rejected from this mean motion resonance, it starts again to increase, and this also highlighted in the derived stability times. And lastly, two dynamical maps, which were constructed by using direct integrations of test particles. This shows the inner part of the Kuiper belt with the most important or most numerous free to two mean motion resonance with the TNOs also depicted in the figure being captured in a long-term mean motion resonance. And then that's the outer part of the Kuiper belt, also showing some very accentuated mean motion resonances, like the 2-to-1 mean motion resonance. All right, and since I think I ran out of time, about the summary, I already highlighted the importance of our research. That's why is it important to study this outer realm of the solar system in terms of dynamical stability. All right, so thank you for your attention.
Thank you very much for the nice talk. Some very quick questions.
Sorry, it was not clear for me. Maybe I just not concentrated that which was data and which was the simulation part. And if you have the data, what is the correlation between that?
Yeah, so the data, for example, in these dynamical maps were these 4,000 TNOs. Their orbital elements were downloaded from a database, the GPL Horizons database. And these dots, these pink and blue dots are these TNOs, so the actual bodies in the outer solar system. However, all the other points in these figures are not simply, but test particles, so the simulations.
Okay, thank you. So I suggest to move on. So thank you, Emesha, again. And our next speaker is Untitled. And he's going to talk about massively parallel tensor network algorithms.
First line. Csak az öv miatt egy kicsit vastag. Hátra. Ah, super. No. All right, so hopefully you can hear me very well. My name is Andor Mencer. I'm a PhD student at Eötvös Loránd University. I happen to be a programmer, but most of you here are physicists, so I will keep the introduction brief because I think we already know what the spins of electrons are, but still just a quick rundown of the stuff we have to know beforehand. So electrons have this property called spin, and it's called spin because we can imagine electrons as tiny spinning balls, with the exception that they aren't really balls and they aren't spinning either, which makes things a bit confusing at first. But it's called spin because regular objects have this property called angular momentum, which they gain by the activity of spinning. And electrons innately have this property, but it's not something they gain, it's something they simply have by existing. So some people, because of this, some people like to refer to this property as intrinsic angular momentum to differentiate it from the classical version. But the property itself is very similar to the spinning version. So instead of saying they are spinning left or right, maybe we should say they are aligned with or against a particular magnetic field, and that way we can take the spinning stuff out of the equation, and it suddenly makes much more sense. Okay, so the alignment compared to the magnetic field can be described via a half integer number. So to sum it up, we have electrons and some single number, half integer, to describe their spin. So far this is pretty simple, but simple can get not so simple when we introduce quantum entanglement, because each particle can get entangled with other particles of the system. So we can no longer describe individual particles, but only the entire system together. And that causes a problem because we can no longer describe the system with the single numbers, but by entire matrices. And as we increase the size of the system, these matrix sizes increase exponentially, which means even with relatively small system sizes, we can run out of memory. We don't have enough processing power. And not just with laptops, but also with supercomputers. This is a very big problem. So most of the time we want to construct the Hamiltonian, which describes the energy level of the system, and it is also required to get the ground state, which is the lowest possible energy level of the system, or in terms of linear algebra, we could say that it's the eigenvector corresponding to the smallest possible eigenvalue. But similarly to what I said earlier, this is a very huge matrix and cannot be dealt with. So what we do is we can decompose these matrices to smaller chunks and then define a certain relationship between these smaller chunks. And what we get is, instead of a huge whole matrix and whole matrix operations, we get a network of matrices and algorithms dealing with these matrix networks. Also, these matrices sometimes are not actually matrices. They can be a single number, a vector, a matrix, and if we move forward, we can also get tensors. So that's the next step after matrices. I think that depends on the simulation, because these algorithms can be used with quantum chemistry, quantum mechanics, so a lot of stuff. So it's kind of generic. The important part is there's a combinatorial explosion, and we have to decompose it into a smaller network, and the tensor network. So now we understand why it's called tensor network and tensor network algorithms. So where were we? Yes, the exact value cannot be calculated. These are iterative approximations, but they can get very close to the actual whole matrix, to the numbers we would get with the whole matrix operations. And what we get by doing this is, because local operations in the network are only require the neighboring or surrounding matrices for the operation. If we increase the size of the system, then the network size will increase, but local operations still require only the local matrices to be operated on. So the sequence of the local operations might increase, but this is a polynomial increase instead of exponential, and that's a very big difference. So we basically could reduce the exponential running time to polynomial. And because we still have a lot of matrices, millions, maybe even billions, and while they might be smaller, they are still very large matrices and very hard to deal with. So a larger simulation could still take years or maybe even more. And because we deal with matrices and millions of matrices, it's only natural to think of GPU acceleration in such scenarios. But before we can actually utilize the GPU, we need code that is flexible and easy to work with. And we had to restructure our old CPU-based execution, or our older code that was based on a monolithic CPU execution. By monolithic, I mean there was no separation of the algorithm itself, the data, and how we operate on the data. And now these three things have been separated, and they talk with an interface, and one module can be replaced, changed, upgraded without affecting the other three. Okay. So once we refactor the code and it's very friendly and easy to work with, we can finally use the GPU for calculations. With larger matrices, this is super simple, because all we have to do is move the matrices from VRAM, from RAM from host memory to device memory. Some people also refer to this process as downloading the matrices to the device, and then we can simply do the matrix multiplication and upload the result back to the host memory or RAM, in other words. And usually this is a not so sophisticated method, because we are not masking or hiding the IO penalty from the fact that we have to move data between RAM and VRAM. However, in this case, if we are dealing with very large matrices, then the IO penalty scales with square, and the compute itself scales with a cubic relationship. So after a certain size, the IO penalty becomes insignificant. And because we are not preloading data, which we would do in more sophisticated algorithms, we have the entire VRAM available. So this algorithm might be simple, but in this case, this is not just simpler, but also better. And if we have smaller but many matrices, then it's the complete opposite, because IO penalty becomes relatively large compared to compute. And in this case, we do want to hide the IO from the compute. And we can do that by having two threads, one which runs the compute part, and the other one which handles only the IO. So And also they can run in parallel because modern GPUs have an IO engine and the compute engine completely decoupled from each other. So that does not pose a problem. And in this image, we can see matrices. So M1, M9, M3, and so on. Those are matrices, and we need them in memory from left to right. The compute thread currently operates on matrix 3. The IO thread runs ahead and preloads in the background some matrices. Maybe it's 10 matrices, 100, a million. That depends on the matrix sizes, the available GPU memory, and how fast the IO works. So what we want to do is load all the matrices between the compute thread and the IO thread, and the rest, those are not required to be in GPU memory, so they can be cleared. You see some green outside, so not just between the compute and the IO thread, but also outside, and that's because some matrices are repeated multiple times in the sequence, and that's why there's a counter under each matrices or each matrix, sorry. And when the compute thread deals with the matrix, then the counter decreases. When the IO threads meets a new matrix, then the count is increased, and that's how we can keep how many times we have the particular matrix between the compute and the IO thread. So this is rather simple. If they hit 0, we obviously delete them from memory, free up space, and with freed up space, we can once again move the IO thread forward and preload new matrices. So this way we can utilize the maximum amount of memory available. We can hide the IO penalty, and we also load not just random matrices, but the significant relevant matrices that will be required for the next few compute operations. Okay, so we have dealt with IO, but the bigger problem might be with smaller matrices is that we often cannot saturate an entire GPU. So if, let's say, we only saturate the GPU at 5%, then it might be still slower than a CPU, even though we hide the IO penalty pretty well. So if these smaller matrices are the same size, then we can simply group them together, and instead of a single matrix operation, we can do a batched generic matrix multiplication, which works because different but same size but different matrices might contain different data, but in order to multiplicate them, we still need the same sequence of instructions. So it's still single instruction, but multiple data, which means it's GPU compatible. With differently sized matrices, it's much more problematic because the sequence for each matrix multiplication might differ. And that means it would be multiple instruction, multiple data, which is CPU compatible, but not GPU compatible. So, however, because they are similarly sized, there's a lot of overlapping instruction between each matrix. So what we can do is use a different stream for each matrix multiplication. A stream is very similar to a CPU thread. However, they can't run in parallel unless they are executing the same instruction. So we can schedule these streams in a smart way. So, sorry, I will show you the original ones. So in this case, for simplicity's sake, let's say a matrix operation requires only 2 instructions, and each stream is a different matrix multiplication. And we can see there's a lot of overlapping because there's 8 instruction and sorry, there's only 4 instruction, different instruction, but 8 in total. And if we schedule these in a smart way, then each sequence of instructions for each stream remains exactly the same. However, different columns can have multiple instructions as long as it's the same instruction. So we have
stacked instruction A pretty well. There's also a double B. We couldn't do anything with D, and with C, yes, we have C at the beginning and at the end also. However, stream 2 has CA and stream 3 has AC, and we would need to change the order of one of the streams, and that would cause problems. So we can do that. So it's not perfect like the same sized version, but still it's a significant reduction of required instructions. So if those 8 instructions were 8 million instructions and we could reduce that to 5 million, that's a significant reduction. So what I have shown you so far, this is what we're working on. So there are no results yet, but we're in the middle of it. So hopefully next time there will be results. And when we are done with the first phase, we will move to multi-GPU. And when we're also done with that, we will move from a single computer to multi-computer, which is, in other words, HPC. And this is what we want to do. So first, the hardware infrastructure of a HPC environment. First, we have a head node, which sends tasks to different computers, different nodes. And each node has, I can also use the pointer. So each node has many processors inside it. It can be a CPU, GPU, FPGA, whatever, something that can process information. And in this case, it can further do parallelization through multiple CPU threads and multiple GPU units. And every a GPU unit in itself is a parallel device since it has multiple floating point units. So, of course, without proper software, it doesn't mean much. So our software looks the following way. We have output sectors, which are matrix-like structures, and they are completely independent of one another, which means we can send them to different nodes on a supercomputer, and they can be calculated independently, so there doesn't need to be a communication between each node, which is good because communication over Ethernet is relatively slow. So we can just send the task itself, which is very small in size, and then each computer will generate the data and calculate, solve that individual problem, and just send back only the result. So that means there's minimal communication, and each node constructs a result for a different output sector. Of course, in some cases, an output sector can be so large that it needs to be broken up into smaller chunks, and that is also possible because an output sector is basically a summation of other calculations. So we can do, let's say, half of those calculations on one node, half of those on another, and we simply have to add them together. So it still works, and that's the second part. And on a local computer or a node, we still have 3 stages of massive parallelization. So first of all, a single assignment looks something like a tensor equals a tensor something. So we have tensors on the left-hand side, we have tensors on the right-hand side, and we can break those into matrices. And first we do that for the left part, and we will be left with many assignments where we have a matrix on the left-hand side and the tensor on the right. And we can use that to distribute load on different CPU units or multiple GPU units. And then a single GPU, or of course even CPU, can do these two. And these two were the ones I was talking about previously, because these are a single instruction instead of multiple instructions. So these are GPU compatible. Now, of course, all the other ones are also GPU compatible, but only in a way that we send those to different GPUs. However, these two can be done on a single GPU and massively parallelized. So we get those small matrices, but many matrices I was talking about earlier by breaking up the tensor on the right-hand side. And then we get many vector and matrix operations, and those themselves can be massively parallelized through Blas and Lepek. So this is the idea for the future. And now we are focusing on these two. And that's it. Thank you for your attention.
Thank you very much. We have time for one quick question.
I was just wondering whether you use I suppose you use a Q plus for the matrix multiplication.
Yes, we are
right. Okay.
basing all of this with
Yes. Did you use the Tensor cores in QBLAS, or is we're running on normal
in the future,
cores?
we want to try it, but right now we only have access to consumer grade GPUs, and those, but they do have Tensor cores, but only for 32 bits of precision. But for data centers, they have better ones with double precision.
Okay, and just one more. What is the smallest matrix size that you use in the program? When you talked about small matrices,
on the input. So in some cases, we have millions of extremely small sizes, like 10 by 10, and in some cases we have. I'm not sure, but it's very input dependent, I would say. So in some cases we have very large, like a million. I think that's too far. Sorry. I don't want to say something that.
No, I was interested in a small one because QBLAS is not very good for small matrices.
Yeah. That's why we try to do the batched ones and the interleaving with the streams. So yes.
Thanks. Considering maybe only one GPU setup, what is the approximated speed up that you can expect? Okay, difficult question.
Yes, because as I said, there are inputs that cannot be even loaded in a single GPU. So we have ideas for that in the future. For example, we can break even smaller tasks into multiple parts and then distribute them in a multi-GPU setup, and then they can communicate via an NVIDIA link. So it's possible, but there are a lot of problematic areas which we still need to fix. So that's why I'm saying it's an ongoing research, and we are still in the middle of it.
Okay, we are waiting for the new results then.
Yeah, thanks.
Okay, so thank you again. Our next speaker will be Shangfang Deng, and the topic will be critical synchronization dynamics on power grids.
Could you hear me? Okay. Thanks. Okay, now. Oh, okay. Okay. Oh, good. Good afternoon, everyone. I'm Xiongfen Deng from Center for Energy Research. This is a research that I work with my postdoctoral supervisor, Geza Balin from Technical University, and Jeffrey Kaelin from Germany. So yesterday, Geza just discussed how he can use GPU to solve like the oscillatory equations on a neural network. So today I'm going to demonstrate another application of GPU to model dynamics on power grids. And so for power grids, we are going to use second order Kulamodel model. So it's kind of different from the one Geza introduced, which is first order Kulamodel model. So power grids are critical for our human civilization because they are utilized to transmit electricity power. For such kind of networks is typically quite complicated, as the one shown here for the high voltage network in Europe. And so for such kind of network, even though here is already quite complicated, if you look into in more detail, you will see that here with a high voltage network and underlying there, we also have medium voltage network, and also we have household consumers, and also nowadays we have a more and more like green energy plans to the power grid that just make the power grid even more complicated. So it is critical to maintain stability for such kind of power grid so that everyone can get electricity they want. But if we have some instability in the system, and then we lead to blackout, and blackout typically we affect a lot of population. Like for example, this largest blackout in the history affect typically like millions of population and causes like billions of economic losses. So empirically, some study have found that this blackout size, the size of blackout, the statics of the blackout size, for example, in this case, measured by the unserved power in some region, typically can follow some power law. And the power law has this kind of exponent ranging from like 1.3 and here like around 2. So this power law indicates that very large scale blackout can happen that exceed like Gaussian model. Previously, there's already some study using direct current threshold model based on self-organized grid equality. The power grid system is organized in a self-organized grid equality is because there are a balance between the consumption of electricity and the generation of electricity. And so they can this also use this DC threshold model to was able to reproduce this kind of power law. But because it is direct current and it's not very realistic, and in reality, what we have is alternating current system, and our goal is to model power grid with alternating current. And in that case, we also model like the alternating current desynchronization cascade. So the DC threshold model can at most be served as an approximation for blackout dynamics. And so before we study the blackout, let's take a look at the two power grid network we studied. So we studied the US and the EU high voltage grid. These two grids typically contain like from 4,000 nodes to 13,000 nodes. And edges can be also quite large. And then the lateral size are not large actually, because especially like for example, for this EU network, this quantity just suggests that this system is typically a small world system. And also we found that for both these two systems, by measuring the effective dimensionality, the dimension are typically to be from 2 to 3. And so now, in principle, we can use this high voltage network as a skeleton and use empirical distribution for like the medium and low voltage branches, and we can establish even more complicated power grid contain millions of nodes. But in this study, for simplicity, we start just by using the high voltage network here. And so now let's take a look at how we can model a power grid. So in the power grid, we typically have generators and then consumers. And the consumers, like here, it is a motor here. Actually, because we just connect all the generators together, the generators are also can become regarded as motors. So when there's a generator transmit the power from here to here to the consumer, and then we can see they this is a oscillator, and this oscillator has a phase. And once the electricity power is transmitted to here, this because of inertia of this motor will not immediately start to rotate. It will take some time, a delayed time for this second for this motor to rotate. So there will be a mismatch between the phase angle between this generator and this motor. So the larger the mismatch of this phase, then the larger the transmitted power will be. And so there, in this sense, the power that is injected into the generator can be split into three parts. One is the kinetic energy for the rotor in this generator, and then we also have dissipation in the generator. And we also transmitted power from the generator to the motor, and the kinetic energy is just expressed in terms of this form, which gives rise to a second order term, and the dissipation gives rise to a first order term. And as just remarked, so the transmitted power will be like proportion to a sine of the mismatch angle, and that just give us this kind of second order Coulomb model, or a Coulomb model with inertia. And this is just for a very simple power grid, but for a realistic power grid, we have typically, as indicated earlier, we have thousands of tens of thousands or even millions of nodes. And then our big challenge is to solve a very large equation system. For each oscillator, I, we will have a set of equations, and then we have millions of set of equations. In here, we also used a rotating prime, so that the self frequency will be a Gaussian distribution centered at 0. And so the biggest challenge here is to solve the equation, and we need to rely on some numerical solvers like this first order Longicuta solver. And so in our experience, we found that for very large coupling constant, we can rely more on the adaptive solver. And so to boost up the computation process, we use GPU code by utilizing the Vexus library because for the very large set of differential equation, we can vectorize this set of differential equation, and then we can utilize this library's vector capability to perform like addition, subtraction, and so on. And that will give us a very substantial speed up, as will be shown later. So then we will measure quantity like the phase order parameter. And for this phase order parameter, we will need to perform a lot of ensemble averages, and that's also very challenging. And then we will also measure this averaged variance of the frequency. And so here we see that after the system becomes stationary, we can measure this phase order parameter after a very long time. And we can see that this system manifests hysteresis behavior, indicate that here we have a first order crossover. And so our ultimate goal is to simulate the system by thermalize the system first until it reaches a stationary state. And then we will cut one line and see how cutting one line can lead to blackout. Like I will explain that more in later. So, but let's take a look at the benchmarks by using after using GPU. So here, this we just did 3 benchmarks. One is for this square lattice with lateral size of 500, and we simulate up to 500 time step. And here we also simulate the cubic lattice with lateral size of 100, and also for our European Union high voltage network. The orange one here just to show the runtime for CPU, and here we also benchmark the this longitudinal first order solver as well as the adaptive solver. We see that once we use GPU, the speed up can be quite significant from like typically 20 or 16 to even like around 400 times of speed up. So this is quite significant. And so now let's take a look at the effect of one line cut. Firstly, we perform the normalization process by starting the system from the fully synchronized state, and then this system will evolve to a stationary state. And for this normalization process, we observe that the damping factor actually just take the effect of slowing down the dynamic of the order, the phase order parameter a little bit. And then for this frequency spread, we see that this damping factor can render the frequency spread even narrower if the damping factor is larger. So now, if we cut one line from this stationary system, and because we cut one line, then we just introduce unstable perturbation into the system. And so the neighboring lines will also become overloaded. So once any neighboring line become overloaded as a code to this overloading condition, then we will cut these neighboring lines, and then more line will be cut. And so there will be a cascade line value triggered by just one single line cut. But that is not always guaranteed. So we are talking about a statistic average. So now, after cutting one line, we see there is a short transient behavior in the system. If the system is quite vulnerable, like this threshold is quite small, and then we see that phase order parameter will become smaller, hinting that the system is more desynchronized. And then the frequency spread will increase quite a lot as compared to like the value from here. And so there's also another quite interesting behavior we just observed from this phase order parameter. We see that even though for some threshold value, we cut the line, but the system actually rendered a little bit more stable in phase order parameter sense, because you see that for this p equals 0.8 or maybe anyway, you can see there's a small increase in the phase order parameter. So we quantified that and found that that is indeed the case. Like in the US power grid as well as the EU power grid, if the system is not very strongly coupled, like here, we see that for certain intermediate range threshold value, the comparison between the phase order parameter of the line cut with the phase order parameter without line cut actually increased. So that is quite kind of unexpected, because actually what we usually should expect that is that all this value will be below this dashed line, but here we see that they can also become larger. And Also, similarly for the EU network, and we see that there are a lot of peaks here, and the peaks are just in a code with the peak for this fluctuation here, and so that means that this peak are just come from the critical state of the system. So to understand this, we can interpret this phenomenon as follows. So because if the system is not very strongly coupled, and so it becomes quite is vulnerable. And if you cut one line, that will trigger some intermediate, that will trigger some cascade-like value, and that will make the network become less connected. And then further, we make the value difficult to spread. And so then in some mediate value for this threshold, we will observe a peak. And so in the following, we also study like the cascade value. The cascade value, for cascade value, we measure number of paired lines and the statistic. And in the vicinity of this critical regime, we observe that depending on different threshold value, we have these power laws as typically observed in empirical systems, and the power laws manifest continuous exponents. Like here for the US is just from 1.1 to 2.1, quite close to the empirical exponent value. And for EU case here, we actually have some larger value exponent value as well, but still quite close to the empirical observed exponent value. And so especially for this task, we found that it is quite crucial to have GPU support, because if we want to obtain these statistics, we typically need to have more than like thousands or even tens of thousands runs to have a good statistics. Otherwise, the statistics will be very noisy. And so then we also observe that unlike, for example, like here and here probably. So we found these bumps. These bumps are just like very large scale blackout, and typically they should be quite unlikely, or it is already quite unlikely if it is following power law. But now we also observe they are following probability that is even higher predicted by a power law. So these are just the code jargon key events. And so at the end, I also show that once there is a light cut, the system becomes unstable and there is some homogeneity in the system. And this is typically in the synchronization community code chimera state. Here is the chimera state for the frequency spread order parameter. And so then at the end, I give my summary. So in this study, we showed that the synchronization and desynchronization of alternating current power grid could be best modeled by the second order Coulomb model equations. And we showed that this second order Coulomb model equations can be speed up. The solving process of this equation can be speed up by utilizing GPU power quite substantially. And we also found that the damping factor just slow down the dynamic of the order parameter, but would be desirable for achieving better frequency entrainment. So at the end, we show that after let the system undergo a summarization process, and then we perform one light cut in the system, then we trigger cascade like values. And for moderate K and T value, there are some isolating effect, which even if we introduce a light cut, the system may become stable in a phase order parameter sense. And then in the vicinity of the critical parameters, we found that the cascade like value size follows some non-universal power laws, which is just our initial goal to use the second order model to model power grid dynamics. Okay, so I finish my talk here. Thank you very much.
Thank you very much for your talk. We are unfortunately slightly behind time, so if there is one question, so super, then I can ask. Nowadays, that there are more and more solar panels also in the big cities, it can be very significant just to have a small cloud passing through above the cities. So can your model be used to predict such effects so that the power suppliers can prepare for such things?
You mean using use our model to model like a solar panels?
No, the effect of if a cloud passes away, then a lot of these solar panels just won't produce any power, and that can have a significant effect for the whole power grid.
Yeah.
So do you think that such effects can be predicted?
Predicted?
Yeah.
As far as I know, so I made like that kind of knowledge, but at least for our model, actually, because our model was established by the best as an effect that like the generators and the models are oscillators. So as for the power generated from a solar panel, because there are no oscillators, so it cannot be described by our equation here. But they indeed just introduce a lot of instability to the system, because usually we just combine a lot of power providers. These power providers have a lot of generators, and these generators are coupled with each other. And so by coupling these generators, they will make the power grid to be quite stable. So if there are some like green energies, like solar power or wind power, wind power they just cannot be considered as a regular oscillator. So the instability that can be introduced will be quite large. And there are also some, I only know a little bit about some other studies. They try to modulate this instability introduced by solar panel and also wind farms. And so they are also just trying to introduce some oscillator to the part of the power generated by wind farms and also like solar panels to modulate this sector of energy.
Okay.
And then they can be combined into the bigger power grid.
Yeah, okay, I see.
Thank you.
Thank you very much. So thank you again for your nice talk.
Thank you.
And our last speaker for today, before the closing, is Daniel Nagy. And the topic will be the application of high-performance computing for bubble simulations in sonochemistry.
So good afternoon, I'm Daniel Nagy. I'm from Budapest University of Technology and Economics, and I will talk about applications of high-performance computing for bubble simulations in sonochemistry. Well, I know it's late in the conference, so I won't bore anyone with the formulas. I haven't planned to show too many formulas. I will just discuss the interesting parts of my research. So what is sonochemistry? Well, the essence of sonochemistry is to increase the yield of chemical processes in a liquid by using ultrasound irradiation. That means that we have a container with some kind of liquid, and we use ultrasonic transducers to create an ultrasound. And basically there are tiny bubbles in this liquid, and these tiny bubbles begin to oscillate. And through these bubbles, we can actually make chemical reactions more efficient. So there are some potential applications, and that's why we are actually doing this research to make those potential applications actually possible. One would be the production of nanometal particles, but perhaps more importantly, sonochemistry can be used to come up with new, greener chemical technologies. Well, but there are some problems. Well, sonochemistry only works right now in the laboratory, so there's a problem to scale up the phenomena to industrial size. That would require the simulation of a sonochemical reactor, and the reactor can contain millions of bubbles, and those bubbles can collapse and collide with each other or break up. And right now, the breakup of the bubbles is an open question, so we don't know how it really works. And in my research, I'm trying to create a CFD simulation where we can actually observe this previously unmodeled phenomena, so this bubble breakup. So let's see what is really happening in the fluid. So we have a bubble. Oh, there's a laser. Yes, so we have the bubble here. It's a gas bubble in some liquid, so it's white. We have the liquid here. Well, due to the acoustic irradiation, which basically means the changing pressure, the bubble starts to expand and collapse and basically starts to oscillate. So we can see the radius time graph here, and we can see the pressure time graph here. And during the oscillation, bubble collapses can occur, as we can see here. And as we see, the bubble radius changes rapidly, and because of this rapid change of volume, the pressure and the temperature increases. And the temperature can increase thousands of kelvins, and basically with this high temperature, we can induce chemical reactions in the liquid. And we can also see that it is possible that the symmetry of the bubble is lost. And then there are some smaller oscillations after this bubble collapse, and then it starts all over again. So basically, that's what millions of bubbles are doing in a chemical reactor. Well, I would like to simulate just a single bubble and see how it behaves. But we can see that it's actually quite problematic, because we have two compressible phases, liquid and the gas. And if anyone dealt with computational fluid dynamics simulations before, they probably know that we don't really like compressible simulations, and especially not two-phase simulations, so it's a real difficulty. And then there are also rapid changes in the boundary of the bubble. So, for example, throughout the bubble collapse, the radius changes rapidly. And there are also large-scale differences, because these bubbles are actually a few microns, tens of microns, and the reactor would be, well, some centimeters. And in my research, I use the Alpaca solver. This is applicable for compressible multi-phase flows. It uses some fancy algorithms to track the phase boundary and to do adaptive meshing. I won't go into details on those. But also the computational requirement is large, because it's actually a direct numerical simulation software, which means that actually there's no turbulence modeling. The turbulence is fully resolved in the simulations. And the code is parallelized with MPI, and it's written in C++, and it's completely open source. It was actually developed by the Nanoshock research group at the Technical University of München. And so our research group at the Budapest University of Technology, the sonochemical research group, actually we are working together with them. Basically, we are beta testing their solver for our case. Yeah, so we are working together with them. So let's see the simulations now. To simulate a single bubble, I use this layout. So we have a container with the water in it. An ultrasonic transducer is placed here. It basically means a time-dependent boundary condition. And there is a bubble in the middle. The most important parameters are the bubble radius, the frequency, and the amplitude of the excitation. And basically, the change of the bubble radius can be described by a simpler model, the so-called Kähler-Mixes equation. It's a second-order ordinary differential equation for the bubble radius, and I will use this equation for validation. And of course, from the simulation, we can also deduce the bubble radius. And there is the validation, basically. So here with blue, we can see the result of the Alpaca simulation. So here the bubble radius is plotted, and with red we can see the Kähler-Mixes equation. We can see quite good agreement for these parameters. Actually, we should observe that the change of the radius is not too large. So for this parameter domain, when the bubble doesn't do large oscillations, then the Alpaca software works very well. It's also possible to do the simulations in 3D. Well, here I put the bubble in a 3D domain, and well, actually it's quite similar. We can see the results here. And here we can observe that the simulation is very short, and that's because well, the computational requirement in 3D is huge. So let's see the details on the computational aspects of this work. So to create a 2D axisymmetric simulation, well, there are usually 10 to the power 4 or like 100,000 cells, up to 100,000 cells. But the time step of in the simulation is extremely small because we have to simulate the propagation of the acoustic waves. But it is an inherently transient phenomena because we want to see what how the bubble behaves in time. So we have to create transient simulations, usually a lot of time steps. And to create a single time step, it's usually up to 500 milliseconds. But then the complete runtime would be a few days, let's say. Well, in a full 3D simulation, then we have 2 orders of magnitude more cells usually in the simulation. But of course, the step size and the number of steps are similar. And then the whole time is usually, so for a single step, it takes a few seconds to create a single step. But then the runtime would take, well, days or weeks. But of course, this is just very rough estimates. Exact parameters depend on the parameter, the resolution, and the complete configuration. And we can see a real problem here that, well, in the 2D axisymmetric case, the number of cells is not too large. And even in 3D, it's not large enough to parallelize the problem efficiently. But on the other hand, we have to do more than 1 million steps usually, and we cannot parallelize the steps. But we can see that some parallelization is possible. So what I did is that I found an optimal way, an optimal running configuration where like we don't really waste compute time, but we still get some usage of the parallelization. Well, to do that, I did a scaling analysis, and the scaling on a supercomputer is described by Amdahl's law. So basically, with this formula, where f is the theoretical speed of a problem, and n is the number of CPU cores used, and p is the parallel proportion. And with that, well, if we know p, and we know how, and then we can basically calculate the speed up for any n, so any number of CPU cores. And which is very interesting that actually if p is only, let's say, 0.99, so 99% program is 99% parallel, well, we can use more than thousands of threads or cores, but we will never get more than 100 times acceleration. And in my research, I used the SuperMQ NG supercomputer in Germany. It's actually the 26th largest supercomputer. And I can use up to 16 nodes, and the single node has 48 cores. The largest limitation on the supercomputer that they only allow the single job to run for 48 hours, and that can be problematic, as we will see later. So I did a strong scaling analysis of Alpaca for these bubble simulations. So the strong scaling basically describes how the speed up change if we increase the compute resources. So I did for 3 different simulations. Here we can see the number of cells. So it goes up to 6 million. Well, when we have 6 million cells, the parallel part was around 99%. That means that, well, theoretically we could get 100 times speed up, but it usually doesn't really worth it because that would require maybe 1,000 core. So instead, later in the simulations, based on that, I stick to this to use around 200 CPU cores, and that was enough to basically reach the maximum possible parallelization for the problem. And here we can see the actual simulations. So there are the parameters. So here the mesh contains 6 million cells, out of which more than 500,000 are in the bubble. We can see the bubble here. Well, the time step is extremely small. And just to simulate less than a single period, it took 7,000 CPU hours, and we can actually show what the result of the simulation. So here we can see that the bubble starts to oscillate in 3D, but that's it. So that's how long the simulation is, because it already took 7,000 CPU hours to do that. I did some more simulations for the 2D axis symmetric case. And actually, what we are really interested in is not when the bubble stays spherical, but when the spherical shape of the bubble is lost. That means that basically, depending on the parameters, different axisymmetric surface modes are possible. So that means we can observe, depending on the parameters, oscillations like this, this, or this. Well, there are other shapes are also possible. Also, the superposition of these shapes are possible. And I could actually reproduce these axisymmetric mode shapes with the alpaca simulations. And we can see the second mode here, the third mode here, and the fourth mode here. And to create those simulations, it only took like approximately 1 day to create a simulation on a single node on the supercomputer. So that only means 48 CPU cores. Well, another interesting thing is that, yes, this bubble can break up. This bubble breakup happens if the amplitude of the mode becomes too large. For example, for the fourth mode, well, something like this can happen, that this mode amplitude keeps increasing, and this can lead to a bubble breakup. And this can also be observed in the simulations. And there is another case for another parameter. Oh, here it's actually interesting because here we have a symmetry axis. So actually we get to torus-shaped bubbles. The most important literature I used can be seen here. So just to summarize, well, the main problem for me was that the number of cells in the simulation is not too large to really utilize supercomputers. That's why using only a few hundred CPU cores is enough, and I could only reach an 80% speed up. And that's because, well, we have to take a lot of time steps during the simulations. Yes, and so I did simulations in using the axisymmetric model and also in 3D. But the 3D simulations, as of yet, not too long. But of course, I plan to do more detailed 3D simulations. Thank you for your attention.
Thank you very much. Are there any questions?
A quick one, just how you generate this breakup? So the microwave is generating a plane wave, or there are multiple sources in the volume, or?
No, there is it's all the same. So there is a single transducer, so single standing wave. There's a standing wave, and the bubble is in the antinode, so where the pressure change is the largest. Yeah, and well, so it's actually all the same as when the bubble doesn't break up. We just have different parameters. So the bubble, for example, is a little larger, but like we have still the same excitation. But if the bubble is too large, it can happen that it breaks up.
Okay, thank you.
So if there are no more questions, then sorry. Of course.
So, am I correct that this is a CPU-based simulation?
Yes, it is.
Okay, so have you tried to look at other computational field libraries that are actually GPU accelerated?
Well, I don't think here GPU would be too helpful, because here we require a lot of communication between the threads, like really a lot. So after every time step, there needs to be a communication between every neighboring cell. Well, here we have like compute domains, and every compute domain has to communicate what happens on the boundary.
Yes, but neighboring communication can be very efficient on GPUs. So I would recommend to look into that. Maybe it won't help, but it's worth a try.
Okay. So last chance. If not, then thanks, Daniel, again. And thank you for all of the speakers for the work conference. And I ask Gergely to say some closing words.
Okay. So this is the hardcore who are still here. First of all, let me just make a brief summary. So we had 2 days. I hope good food and nice talks. So altogether we have 31 talks during this 2 days. We have, I mean, we just counted with Gabor. So we have about 90 participants from here and from outside. All together, we have the YouTube link and the Zoom as well. And I was very happy that more than 12 institute has been signed for the for this GPU day. Of course, the whole event wouldn't fly with some supports which we got from the Lombic Limited, and hopefully you will see the nicely cutted version of these videos in a few months from now. We got also support from the Statcog Limited, thank you very much, and NRDO, and of course the Stream HPC, which somehow very well connected with us. And of course I have to acknowledge my co-organizers, Gabor, Balázs, everybody Balázs, so it's Balázs Szigeti, Balázs Kacskovics, and of course Balázs Majoros, but the one who spent and seen all the talks was Ferenc Vocelka, who was the only one who never skipped any minute of the talks. So thank you very much for all of this. Okay, so now we are closing. So that was the 12th in the series. I hope the 13th will be very good. The 13 is my favorite number. So I hope this will be kind of very big event. And thank you very much all of your contributions, and see you each other. And you are very welcome to apply for the possible grants in the GPU laboratory to use the machines or support some of your young, fresh brains. And let's see each other somewhere in the space-time. Thank you.